You are early. Good job being early birds.
Hey,
David,
early
please tell
birds.
me it's working.
I'm still staying countdown. I don't know why.
I don't believe it.
I blame YouTube.
I don't see the countdown anymore, thank goodness.
Well, that's interesting.
Refresh?
Yeah, refresh. Okay. All right. Now I see it. Maybe it just took like 30 seconds or whatever to propagate from.
Yeah, it's awkwardly slow. And the good news is we're not going to make, well, other than the people on this call right now, we're not going to make everybody sit in awkward silence while we try to turn it on and off again. I'm
No,
glad that
but we
works.
we are going to need music for the break, apparently, unless we do another
That's
water
true.
cooler. So
I nominate somebody else for music. I don't know if y'all want to listen to Frog Banjo, but maybe.
Frog Banjo sounds pretty good. So
It's life changing.
I get my banjo out and play along. So
Do you really play? I've been learning.
so my one of my life goals is to play as many instruments as possible, as poorly as possible. And couple of years ago, my wife contributed to that by gifting me a banjo as a Christmas present. So I have one. It's the same thing I can tell people when they ask me if I play golf. I have clubs and I've been skilled in their taught in their use, but I'm terrible at it. So don't ask me to play, but I will hold it up muted on the stream, and it looks like I play banjo. So
That's beautiful.
yeah.
Yeah.
Oh,
Uh, Nick,
Oscar.
yes.
Well, this is off topic. Go ahead and do the on topic thing.
Oh, no, mine wasn't on topic either.
Oh, okay. Well, this is the type of keys that I think you would really like. These are
The
Xylants.
bananas.
No,
Xylence?
Xylants. Yeah. If you guys mentioned you wanted it to be quiet and not too loud, so these are Xylants that I didn't do anything too fancy on the mods. I did lube them myself, which is key. That's why it hurts me to hear when people are using just factory browns. It's like those weren't treated with love. They're gonna have some going on. Anyways, we were talking about keyboards before we started the stream, and now hopefully people know they can send me their keyboard pictures because I want them
Okay. And how do you spell silence? Is it
with a Z.
okay?
It's like silent,
Yeah.
but that S is silent. Okay. All
Okay.
right. I think it's about time for us to get going. How is everyone doing this awesome Plumber Summit Day 2? Excellent. Love to see it. So once again, I would like to welcome everyone to the Bytecode Alliance Plumber Summit Day 2, February 26th, 2026. Um, and I would like to remind everyone that all the sessions today are going to be recorded. And so if you're not able to catch them, if you're not able to stick around all day, that's okay. They will be posted to the Bytecode Alliance YouTube. Whether you're watching on YouTube or you're here with us in the Zoom call, please use our Zulip topic. Either of them is fine for any chat related to what we're going to be talking about today. With that, here's what our agenda looks like. Up first, we're going to have Nick coming and talking to us about compile time built-ins and Wasmtime. It's going to be very exciting to talk about. Followed by Chris with guest debugging and Wasmtime. Nick's going to join us again to talk about handling, out of memory handling in Wasmtime. We'll take a short break and then we'll get into some lightning talks. So we'll have Pat with a follow-on for the February 24th security disclosures, presumably the Wasmtime ones. Chen, the tool and library for WIT component virtualization. Till Schneidereit, writing good specifications for WASI. And then we'll do a little bit of wrap up at the end. And with that, the most important thing, our wonderful Bytecode Alliance Code of Conduct. So this meeting today is governed by our Code of Conduct. If you haven't had an opportunity, please go and take a look at it. I think it's awesome. Please, everyone, just be kind to each other. And one extra reminder that WASM.io Fix the Year 2026 is happening March 19th and 20th. A lot of us are going to be there. We would love to see you there as well. Please, if you can, get on out there. And with that, I'm going to kick it off to Nick to get us started for the day.
All right. right. And please confirm that you can see my screen.
We sure can.
Great. All right, yeah, so here to talk about compile time built-ins in Wasmtime. So what are compile time built-ins? These are basically a mechanism to allow hosts to implement their own host APIs as WASM components instead of the traditional way of using like linker, func or etc. So this is kind of like a niche instance of the general technique called self-hosting. And then, fair warning, this is all still a bit of a work in progress, not necessarily production ready yet. So tread carefully. So let's jump into an example. So here we have a WASM guest. It's a component. It imports a +1 function. And so here's kind of the traditional way that you would implement this on the host. You'd have a linker, and then you would register a function under the name +1, and it would take some value and return that value +1, right? Boring. More fun is compile time built-ins. And so with this, you can attach these to the code that you're compiling, like to the component that is being compiled or whatever. And you say register a compile time built-in, and you provide a component. And this component should export, something that matches your host API. So in this case, +1, there's a bunch of like lifting, instantiation, whatever stuff going on. But this middle part here, I32 add local get 0, I32 const 1, it's adding 1. All right. So why go through all this rigmarole? What's the big deal? Well, this enables function inlining for your host APIs. So this means that there's no function call overhead from the WASM guest to your host APIs, which by itself is a little bit of a win, but it's not that much. But the big thing is that it unlocks further optimizations kind of based on the call site and the actual arguments and things like that. So for example, calling some objects getter method, which maybe has like an assertion that, something is non-zero or whatever, right? Just becomes a simple field load because the assertion was able to like be statically removed by the optimizer or whatever. If you want to learn more about like all the stuff that function inliners can do, I wrote this article, go read it. So the next thing you might be thinking though is like, oh, my host APIs, the reason they're host APIs is that they need access to host data. Well, we expose to compile time built-ins this thing we call unsafe intrinsics. These are things that look like function calls at the WASM level, but when we compile the WASM, we're actually translating those things into raw inline operations. So these are, loading native loads and native stores, in the endianness of the target, and just raw U8 load with no, bounds checks, no nothing, no safety wheels. So it's kind of up to you to respect the host language's kind of memory model and aliasing model and all that stuff. And then sort of to kind of like root your initial data access, there's also an intrinsic called store data address, which gives you the address of the T in your Wasmtime store T. So this is an incredibly sharp knife. It's very powerful. You can do arbitrary stuff, right? Any kinds of native loads and stores outside the sandbox, whatever. And it's also very dangerous. So preserving the sandbox and safety properties and all that stuff in general is your responsibility. You must ensure that your compile time built-ins are memory safe. They don't expose private data from one guest to another guest or the host's private data to the guest. You need to make sure that they're free of denial of service attack vectors, all of that stuff. And you have to do this for all possible inputs. This includes like when the guest is incorrect and gives you invalid arguments, or completely random data. Like you still need to be robust in the face of that kind of stuff. So yeah, you implement bounds checks, whatever else you need to do in your compile time built-ins before forwarding arguments into unsafe intrinsics. And kind of the rule of thumb is to always assume that the WASM guest is malicious. But kind of the good news, I don't know if it's good news, but interestingly, this is actually no different from traditional host API implementation. You can write sandbox escape bugs with traditional host APIs the same way as if you incorrectly exposed unsafe intrinsics directly to the guest. And so here we have, exposing an arbitrary read function, which takes a integer, casts it to a pointer, and then just does a load. Right? So yeah, what's kind of the holy grail we're aiming for here? Ideally, we'd like to have zero copy and zero function call overhead host buffer access. This is something that people have wanted a lot for kind of the component model and all that stuff, and I believe this is a way to do that. So if we start with the host code, we need to make sure that everything we expose to WASM has kind of known offsets. And so we have repr here. And additionally, if you want your code to be portable, then you need to make sure that the size and offsets are going to be consistent across 32-bit and 64-bit architectures. And so that's why we have this sort of U64 padding going on right here. This is very similar to writing the like VM data structures inside Wasmtime itself, like VM context and all that stuff. And then, so yeah, we can assert our properties so that our code won't even compile if we're on some weird architecture where, this stuff would be unsafe. And we can create a pointer and get the pointer, whatever. And then we can pair a pointer with a length, and that is a slice or, an owned buffer. And again, we have assertions. The extra important ones here are the offset of assertions, because these are the things that our compile time built-ins will hard code these offsets into the code. So if these are wrong, stuff's going to be really bad. And creating one from an iterator of bytes, whatever, it just creates, a box U8 and then kind of pulls the parts apart and puts them into their places. And then drop, it just puts it back together to drop the slice, whatever. And then, we also have a little bit of unsafe code to like, get them as, borrows, mutable or immutable. And then, so here's where we start to get kind of interesting again. So this is creating, a Wasmtime engine and creating a store, and then we pass an exposed buff to as the T in the store T. It's our user data. All right, so now let's look at the host implementation of the compile time built-in in WASM. So the first thing it's going to do is, it's a component, and it's going to import unsafe intrinsics. So these are, all the really unsafe operations. So getting the store's data address, doing, native loads and native stores. And so we'll define a helper that gives us the pointer to the exposed buff. And so this calls store data address, and it adds 0 because it is the thing itself. We could remove that. The optimizer will do it for us. And then len is the same. We've hard-coded 8 because that was the offset before, right? But these are, kind of unsafe, right? So we need a bounds check. And so what this will do is this will check that the given parameter I is in bounds of the buffer's length. And if so, then it will return and do nothing. And if it's out of bounds, then it's going to trap, because continuing would be unsafe. And then what we do is we kind of tie everything together and expose a safe API by first doing a bounds check and then doing, the unsafe native load, whatever. And then set is similar, but instead of a load, we're doing a store, right? And then, yeah, we can also expose len. We could have exposed the underlying thing directly. Doesn't really matter. So now let's look at a guest program that uses this host buffer API. So it's going to be a component, and it imports an instance of the host buffer API, which has, get, set, and len functions. These are kind of the safe functions that we just defined. And it has a main function that's going to loop over every byte in the buffer and it's just going to increment each byte. I don't really feel the need to step through each instruction here, but it's doing a loop. It's incrementing every byte in the buffer. So it does a load of the ith byte, and then it adds 1 to that, and then it stores it back to the ith byte in the buffer. Yeah, so let's look at the benchmark results of incrementing every byte in a buffer via the zero copy host buffer API with compile time built-ins, or the traditional way with linker func_wrap. And it turns out that linker func_wrap is faster than compile time built-ins. Compile time built-ins are like 3 point something slower. What the hell is going on? So it turns out the component model async stuff has lots of state manipulation, and all of that is implemented in Rust right now. And so when we have component-to-component adapters, every call will actually call out to Rust twice, once at the start of the call and then once at the end of the call. And so by switching to kind of component-to-component adapters and inlining those things, we actually doubled the number of WASM to Rust calls happening. Instead of one call out to the linker, we've turned it into a call out to like do a little bit of state manipulation and then do the inline thing and then do another little bit of state manipulation and then return. So hopefully in the fullness of time, this stuff can be implemented inline, and then we wouldn't have these extra calls happening. But right now we can just disable component model async because we're not using it here. Additionally, we defined a bunch of little helpers, right, in our compile time built-ins module, and then they called each other and all that stuff. But by default, we won't inline any functions within the same module because Wasmtime assumes that the producer of the WASM already did the beneficial inlining in kind of the scope of what it could see in the module, right? Which is going to be true if you're using like LLVM or whatever, right? But because we wrote WAT by hand, that's not the case. So we can enable this flag that just does a little bit of extra inlining, and that'll help. And so after that, we can see that things are a lot better. So ultimately, we are 64% or 64 times faster than linker func_wrap when using compile time built-ins and disabling component model concurrency and enabling intramodule inlining. Oh, by the way, this is normalized time, so lower is better, and 1 is sort of like the benchmark of what we're comparing against. Yeah. So maybe, if you're using linker func_wrap, you wouldn't actually like do this kind of, zero copy host buffer API because, it's easier to just take and return a list U8. That's sort of the more natural thing to do in the component model today. So let's also compare that. So here, we're using compile time built-ins. Our previous best thing is kind of the normalized standard now. And it turns out taking and returning a list of U8 is still faster. It's about 6 times faster. And the reason is that the component model requires these various flags to be manipulated around every call. I don't know exactly what flags they are these days because they sort of changed at some point. But they used to be like the may enter and may leave and all of that stuff. And so when you actually look at the disassembly of the adapters that we end up inlining before we inline them, we end up with like an extra load, 2 extra stores, an extra, compare and branch, and then a handful of extra bitwise arithmetic instructions, none of which are actually necessary for what we're doing here. And then additionally, we have that bounds check in the compile time built-in. And crane lift isn't able to deduplicate and lift the bounds check outside of the loop yet. We have plans for doing that eventually and ideas around how to do that, but it's just not implemented yet. And so because of all of those things, when we're touching every single byte in the buffer, copying in and out ends up being cheaper. But what if we're not touching every single byte in the buffer, which is sort of the use case for when you don't want to copy, right? It's like, I'm just going to do a little bit of something here or a little bit of something there, right? So here we're going to benchmark incrementing one random byte in the buffer using kind of the zero copy approach with compile time built-ins versus taking and returning a list of U8. And so taking and returning a list of U8 is the benchmark, or the, kind of the normalized version here. And so switching to the kind of zero copy host buffer API and still using linker func gives us like a 25x speedup. And then we get another 1.7x faster by switching to compile time built-ins and removing the function call overheads and all of that. So they're ultimately, almost 43 times faster than taking and returning a list. So benchmarking TLDR is compile time built-ins and the zero copy style of APIs are faster than linker func when you have these kind of like fine-grained APIs, like I guess like the zero copy host buffer stuff. And they're also faster than copying data in and out of WASM when you're only accessing kind of a subset of that data. I guess that's sort of the same point. And they're currently slower when you're copying data in and out when you're accessing most of the data. But hopefully that is not the case indefinitely. We sort of have plans for addressing that. So the next steps are, the biggest question I have is, I've kind of lost track of exactly what's going on in the component model with all of these flags. And all of these like async and concurrent state checks. Do we really need all of that? Like, is there stuff that we can kind of punt from the component model into user space, and guests that want to catch reentrancy or whatever can kind of implement these checks in user space themselves, and then guests that don't need those things don't have to. Because if we can remove all of this, then that's a really easy way to remove these host calls, and then really easy way to remove all of these instance flag stuff. And so all component-to-component calls will get a lot faster, and compile time built-ins in particular will really benefit. If we don't do that, then we've kind of got our work cut out for us. We need some kind of combination of like static analysis at the kind of component, like the way that everything's getting linked up together and the lifting and lowering pairs and all of that. A static analysis to kind of figure out like when exactly which checks can be elided and when they're unnecessary. And this is a little bit tricky because we also don't really know the body of functions at that time, and so we can't test if they're like actually calling out to other stuff or not, at least without like a bunch of refactoring and probably slowing down compilation and translation to Cliff. Also, it's the kind of thing where, if you accidentally tweak something and then the static analysis can't like prove that it's safe to remove the checks anymore, or the checks do become required, then you end up with these like perf cliffs where all of a sudden things get a lot slower. Similarly, we could also try to greatly improve craneless alias analysis to kind of remove those the instance flag manipulation when we can see that like, oh, we like set it and then we did some stuff and then we unset it. Yeah, it's a bit tricky, but like we can probably do it. Could be nice, might slow down compilation in general, and then also sort of maybe has similar issues with the perf cliffs. And then the other thing that I really kind of don't like is adding like a trust me button, saying, hey, I'm the author of these compile time built-ins and I understand the spec, so trust me that these things aren't needed. The problem is that this is a foot gun because maybe it was true that they weren't needed when you initially hit the button, but then, over time you make little patches or whatever, and all of a sudden, oops, it's needed again, but you didn't realize that, so you didn't unhit the button. Or also just like most people probably don't know the spec well enough to be able to like make that nuanced decision of whether it's okay to trust me or not. Yeah, other random things. So we had bounds checks in there, right? We should probably have Spectre guards for those bounds checks and allow people to do that themselves. This probably means adding kind of a fused bounds check and load or store unsafe intrinsic. We might want to add atomic loads and stores, and unsafe intrinsics for doing that. And then, as mentioned earlier, we need to improve Cranleaf's ability to deduplicate and lift outside of loops bounds checks so that things get faster and nicer. Yeah, and then I guess kind of the other thing is, should we push this into WASI? Should we define like a zero copy host buffer interface and resource in WASI? And once we have that, should we have extend WASI HGP, for example, with accessors for getting headers and HTTP bodies and stuff as these zero copy buffers? So that, if you're in a use case where you're like, oh, I'm actually not going to touch the whole thing. I just want to like check a little bit here or there, or do like some random access, whatever, you can do that. So that's everything I have. Questions, discussion.
There were a couple of questions that came through on Zulip that have largely been answered, but I'll give you a chance to speak to them as well. Yash says, wait, is what Nick is describing made to enable U-ring like direct access to APIs?
I think you could pair this with that kind of thing. I'm not super familiar with U-ring, so I can't really speak to that in too much detail. But it does allow you to share buffers, and then if you have some sort of protocol for when each side touches it and doesn't touch it, it seems like the kind of thing that you could make work.
Cool. Are there more questions from folks? I mean, this is exciting stuff. We've been talking about zero copy in the component model for ages. Till asks, the zero copy buff interface would require host to support compile time built-ins to implement it, right?
No, you can implement it with linker func and in fact, I did earlier. And it can actually still be a benefit depending on, essentially the size of the buffer and the amount of data that's being accessed, right? But compile time built-ins will be faster than the linker func version. And you can also polyfill it. There's nothing that's like requires anything special from the component model. So you can polyfill it or virtualize it or whatever as well. And of course, like to actually get that data to the host, it would still require a copy in that situation or whatever. But from one WASM component to another WASM component wouldn't require any copies or anything there. Yeah.
To clarify what I mean, I understand that you can implement the semantics described in the interface, but you can't implement it in a way that justifies the name zero copy buff without being able to implement.
It would still be zero copy. It just wouldn't be zero.
Right. It would still be. It would just be slower. Yeah.
Yeah, it wouldn't be zero function overhead.
Yeah.
Dave asks in Zulip, if the component model has a native concept of remote buffers that can be optimized to heck, how much of the overhead remains?
Yeah, I guess so. So I just talked about how these things don't require any magic in the component model, like they don't need intrinsics or whatever. But I guess if we did put them in the component model and then added intrinsics for these like get and set operations and the length and everything, then we could just define those things as not doing the whatever state management checks or manipulations or instance flag checks, like the may enter, may leave. And so I guess we could sort of like, spec define our way towards all the optimizations in that case, perhaps. Yeah, I don't know. Like from a like PL design perspective, I don't love it. From a like engineering, just get it fast perspective, it's kind of tempting.
Luke.
Is let's say in my C code I wanted to like take the address of something that's in one of these buffers and then like pass it to just random C code so I could load and store from it. That wouldn't work, right? Because I need to know at each load and store site that I need to call this imports. It's sort of like it's like a multi-memory in a sense, in that I need to
Yeah.
statically discriminate at each load and store site. This one
Yeah.
goes
So,
from the buffer versus normal linear memory.
yeah. So in the guest, you can't treat it exactly the same as, any other pointer or anything, right? So you could kind of think of it as like cherry or something, right? Where it's like your hidden part of the pointer is like which zero copy host buffer am I doing? And then like your loads and stores
Yeah.
are like doing the special thing.
So if you did
Um,
like a fat pointer, that would be a way
yeah,
to solve it.
exactly.
So then you could say if we wanted to have all of our cake and eat it too by maximally optimizing, there's this idea. It's in WAMR called shared heaps. We've talked about it with the Firefox folks. They sound interested to do some experiments because it solves some browser use cases like how do I map an array buffer into my WASM linear memory. In that case, with that sort of feature, which I won't go into, then we could map a buffer into linear memory. So then it would just, you could load and store from a normal I32 offset. And then it wouldn't require any static distinction between these are the ones in linear memory and these are the ones out of linear memory. And so that's one thing that we could go if we went, and that requires a core WASM change. And so it'd be beneficial kind of more broadly, but that's one way to do kind of 1 degree better for like, I can just take the address of this and then
Yeah.
and call a random C library that just has normal C code. And it's just like loading and storing from this, but it happens to be this mapped buffer instead of like normal linear memory.
Yeah, that's true. That does ultimately give you better toolchain UX. I will say there are some asterisks there though, beyond just like the standardization stuff that you mentioned. One is that I think this requires like virtual memory in order to like effectively move things around, right? Like if you want to map in a new thing, you've got to like put it there, or you need like soft MMU or something, right?
Well, the implementation, if this gets into the details of, but if you say there can be at most one mapping, one can do it with a cheap branch. So it's a
Yeah,
software emulation, but it's pretty cheap. What we want to get is the actual exact performance numbers, but at
yeah,
least from what we've heard, it can be quite tolerable. And then
yeah,
if you have an MPU, there are some cases where hardware actually can let you do it without like syscalls or TLB flushes or any of that stuff. So that's the more advanced technique, but it
yeah.
can be at modest overhead without um, touching virtual memory or remapping or flushing TLBs and all that.
I will say our embedding is going to want many of these. Um, and we also don't have virtual memory available. Um,
Well, if it's just updating a pointer, you can change mappings like with a single store. So you can change mappings really fast. It's like I want to touch this one, map,
mm,
touch,
mm,
and then touch this one. So it is with it's not without trade-offs, and I'm not saying it replaces or subsumes what you're talking about here. I'm just saying to the earlier question of if we a thing that would let us go a little farther to have like that real like you know it's just in linear memory, so I can just have a pointer to it. That's a thing that
mhm,
could be then lifted into like a buffer type. That could be a component model, just a WIT type. You can just pass around by unique ownership. So it's transfer in, map it, poke at it, unmap it, pass it away, and
mhm.
that would be complementary, I think, for some use cases. Also, it'll take a lot longer. So what you're doing works now, and is great. So
Cool.
Chris says in the Zulip that zero copy buff without inlining is zero copy in a weird sense because it's giving you the U weights one call at a time, the money transfer structuring cheat of the buffering world, which I think that's so beautifully said. Till says, I wonder if lazy lowering could introduce support to lower stream chunks into a zero copy buff like thing as a canon opt. I guess more generally for list of U star as well. Joel
Yeah.
says, again, though, If you can just allocate your buffers from guest memory to begin with and let the host use that directly, no fanciness required, uh, that should be the default choice, in his honest opinion. It does imply magic host powers and isn't virtualizable though.
Yeah, the thing is often the host ends up being forced to do a copy as well. Yeah, but when you can, for sure.
Yeah, to that, Till says that requires much more massive change to everything around it, though, and isn't always feasible at all. Alex.
Hey, so I wanted to call out. I think in chat that was happening. There's an issue on Wasmtime for optimizing these async stuff with concurrence and state changes and all that. So I basically wanted to call that out. I think it's 12311. That's got a lot of discussion about possible optimizations there in terms of things of refactoring we can do on the async side of things to push more stuff inside of VM context style business. And then additionally, I think it would also remove some of the extra state manipulations that are happening currently. It's also one where I think we will have to sit down and spend a little bit of time on what exactly all these state manipulations are doing. So some of them are like the async task stuff, but we need to optimize that for other reasons, like stack pointer checks and context getting set. That's all just orthogonal to this. But then there's also the aspect of what am I saying? Like the may enter flags, the may leave flags, like these instant flags that are kind of built into Wasmtime. We will likely have to do some sort of static analysis within Wasmtime on our compilation side to say we don't have to do those. I think it's a little too much to put on CraneLift to optimize those out, but I'm not too worried too much about the perf cliffs there in the sense that like the shape of compile time built-ins are highly likely to fit inside that bucket, and you have to be doing really weird things inside of compile time built-ins to fall out of that bucket. So I think it'll generally work out. And from the CraneLift side, I think on that issue there was I think one or two minor optimizations we need, such as I think CraneLift would need to know that if you basically a little bit of dead store or dead load elimination, I forget exactly which, getting rid of those, but those I think are very tractable for CraneLift to do, as opposed to like brand new alias analyses.
Yeah, so right now, CraneLift will eliminate dead loads and replace them with, a use of the, I guess, well, yeah, we'll eliminate dead loads if they're trusted and won't trap or whatever. And then we'll also replace redundant loads with uses of the previous value. We don't eliminate dead stores because that's a bit harder and that's going to require work. But like, I don't know, it would probably be nice to have anyway. Yeah, I don't have a great sense of how much compile time overhead it might impose though. And I guess like this is kind of opens a question in general, which is like the more sort of stuff like if we're going to do static analyses based on right now we do static analyses at the WASM component level just based on like the linking and everything and the instantiation, right? And then like each function body is still compiled kind of independently. And when we're doing the analysis on the like linking and all of that, we don't know the contents of the function body. So we don't know if it's like going to make any calls or not and is potentially reentrant or whatever, right? But like the more we kind of push on this, like the more maybe it makes sense to like actually inspect the WASM body at that first initial static analysis time, if that's going to give us better results or whatever, right? But then how much is that going to impose to compile time overhead? And like, do we want to like have an O3 or something now or what, right? Like, I don't know. There's like, I feel like there's a whole discussion around like, how much do we want to push the architecture towards like more, better code gen and worse compile times. Obviously, like limiting that as much as we can, but yeah, there's a conversation to be had there.
I definitely agree with that. And in my mind, the goal is to get to the point that a sync to sync, component to component call, which is what's happening here, had literally 0 instructions of overhead. And so I think, I personally, I think we should definitely be able to get there. But we'll have to figure out how exactly.
Also, did we already even remove kind of with the spec changes at compile time the recursion check for component to component calls already?
We did, yeah. That we kind of went. There was a bit of a back and forth where we kind of went. We took, I think, one step forward, and then we took one step backward in terms of costs involved there. So we like removed stuff, or we added stuff, then we removed other stuff that ended up being similar costs. But yeah, so those are gone. We still have a couple of other minor things, which honestly might just be outdated, and we can go back and like statically remove those as well. we haven't really given them a whole lot of thought. And so it might not, all the static analysis may not even be necessary. The component model changes might be sufficient for removing some of these flags. We just haven't revisited them.
Yeah. I have tried to look at the component model spec to find all of the flags and like sort of their motivation, and I've come away like not having found them. So it would be really useful to like have a place where we have kind of like compiled, here's like everything that an adapter must do, and like here's the motivation for why also. Because like that's my next question, right? Is like, okay, I have to do this. Like, do I really have to? Like, can we not? So I don't know. That would be really helpful for me, but I also see, that's work for someone to do.
Well, I would say that I think the document you're looking for used to be the component model spec, and then the spec changed, and we haven't caught up in Wasmtime. So I think that's just a lot some catching up work to do there.
We've got another question from Dave. How optimized is the current async state transition stuff? Is it at a first implementation level that satisfies the spec as cleanly as possible, that is optimized for spec compliance rather than performance, or is it already optimized decently? Given the huge difference in bar heights on the graph, I'm just trying to understand if the big bar is just an effect of the current implementation or it's necessary by design.
I'll take this if you want, Nick.
Yeah.
I would describe it as what's necessary to satisfy the spec currently. So it's not heavily optimized, and I think it contributes to the very large bar. What Nick was showing before concurrency support was disabled, that is sort of what you would see right now. It's a little bit worse for if you call it async function. So Nick's doing the absolute optimal case from a static point of view of a synchronously typed wit function is synchronously lowered and synchronously lifted, and all of that's being fused together, all synced, no async whatsoever. And even that is still this exactly we got, well, I think this 3.5 times slower. Once you start adding async to the mix, so async lowerings, async types, things like that, it gets a little bit slower as well, in the sense that we have to manage some fiber stuff. We call out for the host for doing a little bit more heavyweight operations. So that'll definitely need some work over time. But I don't think that would affect this compile times built-in work, in the sense that unless it seems, at least in my mind, it would be pretty unlikely you're writing an async compile time built-in. And while it is possible for a component to async lower your compile time built-in, the expectation that would be fast is not really on the table. It's fine. It just works as opposed to being the fastest thing possible.
All right, we got any other questions?
Also, just add, I think a big part of that big delta was those host calls. I mean, adding a host call in a very hot path is going to dominate. I think they've been eliminated by design now. Like, that was a spec level change that motivated that killed those by design in component to component calls. So even though there's still more work to do, I think the biggest, fattest part of that has already been lopped off. Is that right?
I would describe it as kind of two halves. One was we did require some for the reentrancy checks to host calls, and that has now gone at the spec level and has gone at the translation layer, and that's why if you disable the concurrency, it goes away. We have the other half though of managing the async task stuff, in the sense that we still have to call out to the host for that, and that's not gone from the spec level. And that part is the one where we have an issue about optimizing that and making it so we move all of the task manipulation into the trampoline, and all of that can be very easily rolled away by crane lift.
Yeah, I think there's sort of two layers. It's like, first you have to like get it out of the VM and into the inline trampolines, and then we can optimize it. And that can probably remove a bunch of it, but probably not everything on its own, right? And then there's like the static analyses to like, let's not even emit code to do whatever flag if we don't need to, right? And for that latter part, the static analyses, I think it would be also really useful to like get precise preconditions for when we can elide things or not, because that also seems like something that's somewhat ambiguous in my mind, at least.
Yeah, that one I think we definitely need to sit down and kind of just do a little bit more thinking on the Wasmtime side of, do we, like exactly what you're saying, of do we even still need this? And then I don't think I do think that's a separate bucket from the async task manipulation, and but I think it's definitely tractable.
Cool. Anything else?
Which, we've taken a lot of questions and comments. I haven't heard any concerns from anyone. Someone throw in a concern. Going once? Twice?
I'm deeply concerned about how fast this is going to be when it all works.
Oh, yes. Deeply concerning. Excellent. Well, thank you so much, Nick. That was absolutely riveting. And so we're going to keep moving right on along over to Chris Fallin. Guest
All right.
debugging in Wasmtime. Oh, baby. Let's see it happen.
Indeed. I hope I can live up to Oscar's excitement for this topic. Let me share my screen. And view a slideshow. So I'm gonna go fast because there's a lot to talk about here. Yeah, but please feel free to ask questions in Zulip as I go. So guest debugging in Wasmtime. Here's what I'm going to talk about. I'm going to talk about what it means to debug at various levels of abstraction. I'm going to talk about what I built, which I've split into a bottom half and a top half. That'll make more sense as we go along. I'm going to give an actual demo of LODB attached via GDB stub to Wasmtime, debugging code. And then I'm going to talk about future work. So what does it mean to debug WebAssembly? So you start, by writing some code in some language like Rust or C, and then you'll use a WASM toolchain to compile this into WASM modules, WASM components, and then you'll run this in some WASM VM like Wasmtime. And typically, if that's not an interpreter-based VM, that will do some compilation, either AOT or JIT, into compiled machine code. And so you have these three different levels of lowering at which your code is represented. And you could look at the code that's produced at each of those levels, right? At the source language level, it's, function main. At the WASM bytecode level, at least for typical compiled languages, that'll become a WASM level function. And at the compiled machine code level, you can look at the machine code that's actually produced. And you can imagine debugging at each of these levels, right? So you might want to single step through each of these abstraction levels. So if you debug the source language, you might want an experience that looks something like what you see in a host native debugger today, right? You set a breakpoint at the main function. You have source locations, main.rs line 10. You can print source level variables. So we'll call this source language level debugging. There are also use cases where you might want to debug the WASM bytecode, right? So I might want, and this is a pure hypothetical, sketch right now, a debugger where I can set breakpoints at WASM functions and see breakpoint locations in terms of bytecode offsets, and actually look at the WASM locals and globals. That would be pretty cool for certain categories of use cases. And maybe even disassemble the bytecode. So we'll call this bytecode level debugging. And then you might want, in other use cases, to be able to actually debug the machine code. And so this machine code in an environment like Wasmtime will be not just the WASM functions compiled to machine code, but will be calling into the Wasmtime runtime as well. And so sort of necessarily, if you're debugging at this level, you're going to see the calls, the transfers of control back and forth between both. And so we'll call this kind of debugging machine code level debugging. So who are each of these kinds of debugging useful for? So source language level, I would say, is most developers, most users of Wasmtime that we're targeting. This is the 95% use case, right? To them, the WASM runtime or the WASM platform is kind of irrelevant, like the kernel for native platform development. It's just where the code's running, but really you care about debugging your code. Debugging at the bytecode level and actually seeing, single stepping through individual WASM instructions would be pretty cool for people who are building WASM toolchains, right? So if you're writing a new compiler that targets WASM, this might be useful for debugging your compiler's output. Also performance sensitive WASM developers, right? So you might want to see the WASM bytecode and what it's doing in the same way that performance sensitive software engineers look at disassemblies of native code today. And then machine code level, right? So this is mostly just useful for Wasmtime developers, I would say, and there are dozens of us, right? So that's a little bit glib. Like it's also maybe useful for people who are doing low-level performance work that depends on understanding what the runtime is doing as well. But there are a lot of downsides to that view as well. And so today we only support machine code debugging, I think because of some sort of like path-dependent reasons or economic reasons, I would say, it was pretty, expedient and easy just to allow attaching a native debugger to Wasmtime and emit enough metadata in order to allow that to see something about the WASM. And it is useful, especially for us as runtime authors, right, to be able to see that, what the code is doing and debug it and how it interacts with the runtime. But it has a lot of downsides. So it's pretty flaky. There have been a stream of issues over the years with the bugs in our door translation, values optimized out. In general, providing perfect fidelity debugging with an optimized compiler is a really hard problem. And it's also confusing for someone who just cares about debugging their own code because you see a weird mix of the Wasmtime runtime with their own code running, right? So you single step into something that becomes a host call, and all of a sudden you're looking at Wasmtime's WASI implementation. And it's also low level in the sense that it takes over the whole Wasmtime process. Maybe that's fine if you're targeting like the Wasmtime CLI itself. But if you have like an embedded Wasmtime in some other context, maybe that's actually not possible or hard to do. And so we can do better, I think. And in fact, I've built a thing that I think is better for these use cases, for these audiences. And so the target here is source language or bytecode level debugging. And the way that we're going to do that is with what's called guest debugging, right? So this is a debugger built into Wasmtime itself that gives you a Wasmtime native view of the Wasm VM as if it's an ISA that you can single step through, and then source language debugging on top of that. And so what do we actually want to build? So let's build, I'm going to introduce this terminology of bottom half and top half. The bottom half is what I call the piece in the runtime itself in Wasmtime that actually implements the APIs that allow, introspection, that allow single stepping, that allow breakpoints, all the things you'd expect in a debugger. And then the top half will be the UI or the interface on top of that. So for the bottom half, right, we want something that allows us to debug WASM on its own as if we had a native WASM CPU down to single stepping through bytecode. We want a fully WASM aware view of the world. So we want to be able to see all the WASM entities, right? If there are multiple memories, if there are GC objects, if there are WASM tables, exception objects, all of these things. And also built into the WASM engine itself so that it gives us a solid platform for things like record, replay, and reversible debugging, which I won't talk about today, but are on the roadmap for sure. And so I'll break down sort of how we built this into and give a few details about the implementation in three different categories. So I'll talk about introspection. And so, that includes things like providing access to all the WASM entities, even the private ones. That one's kind of straightforward, so I won't say too much on that. But the more interesting part of introspection is actually giving a view of the current WASM execution state, right? So that stack, in every stack frame, the current PC, the locals, the operand values, the instance the stack frame came from, the function the stack frame came from, and all of that. And so that requires a lot of sort of insight into how the WASM bytecode is mapped into machine code. And then there's an API for breakpoints. So this involves actually somehow patching the code or getting control back at certain points in execution, which naively is hard if all you have is just compiled machine code. You have to somehow interrupt control and interject and get control back to the runtime. And then a debug event API, which is basically this infrastructure in the Wasmtime runtime itself to allow plugging in something else that gets essentially called from the WASM, morally called from the WASM, whenever certain kinds of events occur. So let's talk about introspection a little bit more, right? So this is a classic problem that every debugger has to solve. Somehow we need a mapping function, right? So you interrupt control flow, you interrupt control, you get a snapshot of the current machine state. We've compiled WASM down to native machine code. So we have the native machine registers, right here, the x86 registers, RIX, RBX, whatever, and we have a native stack frame. And somehow we need to compute what the view of the WASM VM state should be based on that native state. And it's somehow embedded in there kind of mostly, unless it was optimized away. But it's hard in general, right? And so the reasons this is hard is that values can be optimized out. Values may be moved around or rewritten through, typical optimizing compiler rewrites. And so, unless you build your compiler from the ground up to support this kind of like tracking of the injection, the mapping, WASM really loses its identity as the IR is transformed, right? It just becomes a soup of code that's mixed in with all of the other native code. And so there was a debugging RFC about 2 years ago now, spring 2024, that I'll call RFC V1. And the answer in that RFC was to use Winch, the baseline compiler, instead of CraneLift as a backend for Wasmtime for debugging. And the upside of this approach is that it has a well-defined and simple mapping from the machine state back to the WASM state, right? So it actually reifies all the WASM locals as slots on the stack. It reifies the WASM operand stack as the actual machine stack with pushes and pops, and so on and so forth. But it has a lot of other downsides with regard to feature parity, right? So it's mostly x86 only. Recently, they got to feature complete for Core WASM on AIRD64. Doesn't have our other platforms, doesn't have Pulley, doesn't have RISC-V. And maybe even more importantly, doesn't have a lot of the more recent WASM 3.0 features like garbage collection or exceptions or stack switching or tail calls. So we could do all of that. We could bring Winch up to parity, and we probably should in fullness of time. But I started to think when I looked at this landscape that maybe I didn't want to put this on the critical path of getting good guest debugging. And so we can ask the question, how can we reuse all of the work that went into the CraneLift-based backend and build something on top of CraneLift instead? And so the answer I came to is actually kind of this deceptively simple idea. It took a lot of thinking and then realizing, oh, wait, no, we can just do this. And so the idea is let's emit IR to store the values as part of our state, right? So let's look at how some WASM bytecode gets compiled. We'll have, getting a local, and then we'll add 0 to it, right? So an optimizing compiler should see this and say, oh, you're returning x plus 0, we can just return x. Right, so CraneLift indeed will rewrite this cliff, this IR that I'm showing on the right, to not have the add and the constant 0, just return the original value. So you can imagine now if we're single stepping through the WASM bytecode and we stop like after the const to 0, what's the top of stack, right? We've optimized that away, so we don't actually have part of our WASM VM state anymore. And larger and more complicated versions of this are exactly why you see in debuggers debugging, optimized code, the value optimized out, right? You see that classically in like GDB or LODB. And so the insight with instrumentation-based introspection is that we can just not do that. And so basically what we do instead is we define a new stack slot in the native stack frame for every compiled function, and we insert code that actually updates the memory state in that stack slot corresponding to the WASM VM. Right, so after every, let's say, stack pushing operation that we compile, we'll generate IR that does an IR level store into that state, and likewise for locals and likewise for any WASM VM level state, right? So we've sort of turned the problem on its head and said, instead of trying to reverse engineer the output of the compiler and figure out, where something that has disappeared is computed, we say we're just going to compute exactly the output that you want, which is the view of the WASM VM. And so the compiler can do whatever it wants to optimize. This is fully robust against any CraneLift pass we could conceivably build, because stores are robust side effects that must not be changed. That's a compiler correctness invariant. We preserve the state by making an explicit output. There's some detail I'm not showing here regarding sequence points. This does have an overhead. We're inserting a whole bunch of stores to stack frames. That overhead I've measured at about 2x, which is a big hit, but actually that's still better than the 4x that you take by moving to Winch instead of CraneLift. And so we get perfect fidelity in the WASM VM state. So the next thing is this event infrastructure, right? So we basically want to have a facility for registering a handler to be invoked on various events. And I won't go into too much detail about exactly how this interacts with the async stuff in Wasmtime, other than to say you basically register what looks like an async host call, and it gets this debug event. We can add to this enum over time. Right now, it gives you events on things like traps, breakpoints, epoch yields, host call errors, and exception throws. But we could certainly add more, memory watch points in fullness of time. There were a few key design choices that we hit when we were thinking about how to do this. So we sort of made certain choices here to make things a little bit simpler. And so one choice is, how do we actually ensure that the store in Wasmtime is frozen when the debugger has control, right? So what we want is this sort of control flow where guest code is running, and then we hit a breakpoint or some other debug event, and we want to basically have this coroutine like ping pong between the debugger and the debuggee, right? So we freeze the debuggee and we transfer control to the debugger. And then when the debugger says run, then we let the debuggy continue. And so the way we do this is basically saying that it looks like a host call, and the host call gets a store context mute. So at any point in the WASM, when we hit a debuggable event that has, and there's a debug event handler registered, we essentially do the equivalent of a host call and pass in mute borrow of the store. And because of Rust's, borrowing rules, that means that nothing else can run in the store. So there is some async component model stuff that should eventually be done here, making this work with the accessor paradigm that Alex and Joel have built. That doesn't, we don't do that yet. And so what this means is we just freeze the entire store when the debugger is active. And then the other thing that we sort of went back and forth on is whether we actually do host calls or whether we do something smarter with, say, signals, right? So you can imagine keeping the compiled code that we normally have that uses signals to inject like traps. Right, so you hit a divide by 0 in x86, that gives you a sig FPE. You hit an out of bounds if you're doing virtual memory base bounds check, that gives you a sig segv. And maybe we want to somehow intercept that signal and give the debugger hook in Wasmtime control from the signal handler, maybe indirectly. And so the way I actually did prototype this, and the way that this worked is what I called call injection. So in the signal handler, we would actually push a new stack frame. We would mutate the state of the thread that was interrupted. We would push a new stack frame under the WASM stack frame that looks as if the WASM did a host call into the debugger. And so this basically kind of almost pretty much worked in Linux. I wrote the assembly for all 4 of our architectures. But it is really...
You saw the money I moved this morning? That was quick. That was good.
Yeah.
Sorry, could you mute, David?
Because Daniel's...
David, could you mute? Thanks. So it pretty much almost worked, but it's very brittle in the sense that, or not portable, I should say, in the sense that every OS is a little bit different. So Linux gives you the ability to mutate the stack. Windows doesn't because there's no red zone there. Mac OS, you run in a different thread. So you have, anyway, so there are different things you have to do on every platform, a whole bunch of like fiddly assembly. And then sort of the other thing that really killed this is that dealing with point of provenance and store ownership, when you don't have an explicit host call that actually passes in a mute reborrow of the store, is kind of a tough nut to crack. And so basically we went back on that and we said, let's do actual host calls. So fortunately in Wasmtime, thanks to Alex's work like a year or 2 years ago, we have the ability to say we don't do signals-based traps, we do instrumentation-based traps. And so we pretty much just use that. The one thing that's a little bit interesting is breakpoints. So let's talk about breakpoints now. So really, we don't want this world where we like have a dynamic branch at every possible breakpoint, which is between every WASM bytecode instruction. And so native debuggers do something that pushes the overhead to the away from the common runtime case and to the breakpoint insertion case by actually editing code, right? So the way that like GDB will insert a breakpoint in a Linux process is that it will actually edit the .text and it will insert an instruction that delivers a signal like UD2 on x86 at the point where the breakpoint is. And so so maybe that's what we want to do, right? So there are a few design axes that we considered here. And one of them is, do we edit the code? Do we do this thing where we insert new code, which is slow to update, complex, but has low runtime overhead because in the common case, there's no dynamic branch there? Or do we do the dynamic branch? And then the other design axis is actual call or trapping instruction leading to signal-based call injection. So we kept it simple. I already said basically we gave up on the signal-based call injection. So we want an actual call, but we can still do an edit-based thing and insert the call dynamically. And so that's what we did. So I added functionality to CraneLift to have what we call patchable calls. And the way this works is that we put a no-op, no-ops just big enough for a call instruction. So 5 bytes on x86, 4 bytes on the risks. And that is NOPS by default. But we have functionality now to actually edit that and insert a call to what we call the breakpoint trampoline. And this trampoline has a custom API, so it doesn't clobber any registers, right? So it doesn't affect the compiled code. It really is just NOPS inserted at certain points. And this trampoline will save all the registers, and then we'll actually do a real host call. So we reuse all of our host call infrastructure for that. And then we insert all these patchable call sites, and we emit metadata during compilation saying, for this breakpoint at this WASM PC in this module, patch this offset this size in the CWASM with these bytes, which is a call instruction. This required some new infrastructure in crane lift to distinguish between the shared module code, which we now call engine code, and private copies of the code, which we now call store code for every store. And then, yeah, dynamic patching, so unpublish, edit, republish, iCache coherence, all of that fun stuff, all that's handled now. And so now we have the ability to actually turn on breakpoints by patching and call instructions to a host call. And so then single stepping is the other thing you want in the breakpoint universe. And you could do something complicated. I opted not to, and it's good enough. And so the not complicated thing is single step means enable every breakpoint in the module. Yeah, so that's what we do, and it's good enough. So the final thing I'll talk about in implementation detail here is stack frames, right? So you want to be able to walk the WASM stack when the store is paused, the debuggy is paused, and look at all of the debug state slots that the instrumentation inserted, as well as the VM context, as well as the WASM PCs, etc. And so the initial idea with my REST brain on, right, I said, let's build a safe iterator that actually takes a mute borrow of the store, holds that borrow of the store, and then lets you walk the stack frames while the store is borrowed. And so that's fully memory safe, right? So the thing you want to avoid here is basically having raw pointers into the stack flying around that could be invalidated, if the debugger tries to look at them after you have the WASM continue and unwind that stack. But it turns out that debuggers actually do want A, to hold multiple stack frame handles at once, and B, to do other things with the store while the store is frozen. And so this iterator, external iterator that holds a borrow of the store thing turned out to be a little too limiting when I got to actually building the top half. And so I asked, okay, is there a way that I could actually have an entity handle in the same way that we have entity handles for instances, for tables, for memories that refers to a WASM frame, and then somehow intelligently deals with the case where the WASM continues and that frame is no longer valid. And so the idea that I came on is this thing that I'm calling versioning, execution versioning. So it turns out that it's sufficient to say we have one counter, the version counter, which is just a U64 in the store. And every time you return into WASM, you increment that counter. Now, if you hand out a frame handle that is a raw pointer to the stack, like the actual machine stack, but you stamp it, you mint it with the store ID and that execution version. And before using it, you always check that the store is still at that version. That is sufficient to implement lazy invalidation, right? So what that means is that as soon as execution continues, it can only continue by returning into WASM. You might think, okay, but what about dropping futures? That actually returns into WASM and unwinds as well. And so this is sufficient to give us a fully memory safe thing that can have a whole bunch of raw handles under the covers. To use them, you pass in a mute borrow of the store at the time that you use them, so it still respects the rest ownership framing that we have, and so this gives us the ability to basically cache handles at every level of the stack. Okay, so that's the bottom half. Let's talk about the top half. So the vision in the RFC-v1 was this thing called debug adapter components, right? And so the way that this was framed was we could just fall into the dwarf monoculture and say that let's just implement a debugger that understands dwarf in the WASM modules, and that's the end of it. But maybe there are other languages. Some are compiled, some are interpreted, some will be new compilers that can design their own debug format. Let's actually try to foster an ecosystem where you can build an adapter for whatever debug format you have, and sort of ship it with your language. And then Wasmtime could understand, okay, this component has this adapter, that component has that adapter. And then Wasmtime would basically have a multiplexer at the very top that serves something like DAP, the Debug Adapter Protocol, which is a UI level view, right? So it's a very high level view that talks directly about frame variables and evaluates expressions by just passing the string, which is the expression. So it expects all of the smarts to be in the debug adapter. And Wasmtime will multiplex into these different adapters. So, I looked at this when I got to the point of building the top half and realized debuggers are a lot of work. This is hard. And that's fine. Maybe that's the job we signed up for. But there's the question of could we do something maybe that's a little bit easier in the meantime? And so for, just to give a view of what this would take for, classical C, C++ Rust debugging, basically what this would mean is we would need to either take LDB or build the equivalent of LDB, including things like the C++ expression parser, type system understanding, arbitrary expression evaluator, which does JIT, by the way, Pretty printer ecosystem, which involves a whole library, Rust, the standard library ships with pretty printers for like vec and hash map that uses Python. So by the way, we would need to embed a Python interpreter in the thing. And so this is just like a whole bunch to basically, probably borrow from LODB and take apart and rebuild, but that's a lot of refactoring. And so we want something in the meantime. And so in the meantime, actually, while we were sort of thinking about all this, LODB and V8 and JSC, their respective WASM engines, evolved a WASM-specific extension of the GDB stub protocol. So GDB stub, for those who don't know it, is this ancient thing come straight from the 1980s where you have an embedded system with a serial port and you connect your host system to that serial port, and GDB can basically control execution and do debugging, introspect the stack, introspect locals over that connection. And so it survives into the modern time. This is the way that you can attach GDB to, say, like QEMU. There are a whole bunch of GDB stub hosts that are implemented. And it's actually not terrible with this WASM extension. It supports multiple modules, it supports multiple memories. It has this basically synthesized address space that has all of them, in this one address space. And it works, and it's kind of the direction that things are going, at least for dwarf based languages. And so maybe we want to just plug into that ecosystem and take advantage of that. And so I sort of went then far in the other direction and said, let's just build native GDB stub as part of Wasmtime using this bottom half set of APIs. But the compromise that eventually I came to when talking through sort of the ecosystem implications of that is that we don't want to completely hard code GDB stub and cut off the flexibility where someone else might still want to build their own debug format later. Instead, let's do this thing where we still have the bottom half APIs in a WIT world for a debug component to use, but let's give it the WASI CLI world on top. And we call this debug main. And so this gives you a lot of flexibility. This means that you could implement, a full dwarf parser and serve DAP and all of this over, WASI sockets, TCP sockets, or WASI HTTP or whatever. You could implement GDB stub and serve it via a socket. You could implement, a text mode curses interface. You could do an equivalent of like the old MS-DOS debug.com and a machine monitor. You could do anything with this, right? The possibilities are endless. And so this basically is what we decided on. By the way, we as a project haven't technically decided on it. The RFC is open. I posted it 4 days ago. Please go approve it if you agree or discuss otherwise. But this is sort of the plan of record tentatively. And so that is what I built. I built the WIT world, and I built a GDB stub implementation that lives in this world. So I'm now going to Command Tab over to my terminal, and I'm going to show you this running. So here I have, oh yeah, so it's not perfect yet. So here I have a Wasmtime. This is in my own branch. All of the changes that I've made to core Wasmtime, the Wasmtime crate, by the way, are already upstreamed. Thank you, Alex, mostly for all the reviews. The WIT world is not yet, but I will do that as soon as the RFC is approved. I have this -d debugger, and I'm pulling in the GDB stub component, which is indeed a WASM component. And I can show you the world, debugger, debuggy. It has a bunch of stuff, single step, resumption, read and write memories, WASM exceptions. From a frame, I can get the locals, I can get the stack. We have WASM values. So we can do everything we need to do as a debugger with this API. And I'm giving it an arg. So this is the WASI CLI part. You can give it argv. Let's serve GDB stub on port 1234 of localhost. And we'll run test.wasm. What is test.wasm? What is test.c, I should say? It's a little thing that computes the Fibonacci sequence. Okay, so let's run that. I've enabled the debug printing in my thing just so you can see more interesting stuff. See the matrix go by. You need LODB that has the WASM target built in. It turns out that Debian's default LODB doesn't. So maybe we could ship this as part of WASI SDK eventually. And we're going to connect to the process. And we're going to break on main. And we're going to continue. And we see that we're now in main. If I switch back to the Wasmtime thing here, you see it's speaking this protocol. That Q WASM call stack is query the WASM call stack. So this is using the WASM extensions to GDB stub. I can break in fib. I can continue. We're in fib now. Next, PA, PB. I can view locals, psum, and finish. Okay, so that actually is an LDB bug where LDB will die once the command finishes. So that's sort of an interesting thing that I'll need to debug in LDB. But if I connect again, next, bmain, continue, next, then yeah, we should see the result. So printed result, and then we see a bunch of queries. So basically, this is working. It's a little bit flaky in the sense that LDB's support still seems a little bit weird. So again, if I continue, LDB crashes. But yeah, it basically is there. So what's the future work? So after the RC is approved, please go approve the RC. I will land all of the rest of this work. And then there's record, replay, versatile debugging, which I didn't at all talk about today, but that's sort of, continuing work after this. Maybe eventually we'll get to the debug adapter vision, given sufficient resourcing. That is, I think, probably like an engineer year of work to build out. I don't know if I can afford that in my own personal timeline roadmap, but that is something we can talk about. And then there's a discussion question, which is what do we do about our existing host debugging? It's still there. Maybe in the fullness of time, if this covers everything that we need for WASM, we don't need the other dwarf transform anymore. Please discuss. But yeah, that's basically all I had. So in the 2.5 minutes left, I am happy to answer questions.
Yeah, I don't know about you all, but my heart is absolutely racing after that demo. Yeah, so you have a number of folks in the chat who are just very supportive and excited. There's a question from Mindy. Would this debug WIT interface be Wasmtime specific?
It doesn't have to be. We could go through a standards process. If you squint enough, looks like a reflection API, and including things like it could have things like dynamically spawning an instance or a component. And I know there's been discussion about that in the component model as well. So I haven't thought too deeply about that. I kind of just wanted to sprint and make this work for Wasmtime. But that is an interesting sort of follow-up. Yeah.
Any other questions from folks? I'm waiting for someone to say, when can I use this?
As soon as I land it, please approve the RFC.
I guess I have a quick question. Well, first of all, I love the idea of implementing debug adapters using components. I think that's awesome. Are there any drawbacks to doing that?
Yeah, well, so drawbacks versus what, I guess is my question. Drawbacks versus a native hard-coded top half that's in the CLI, or versus what?
Yeah, I guess the alternative would be like some sort of host level Wasmtime plugin, I suppose, to allow multiple implementations, possibly not maintained within Wasmtime. But yeah, I guess
Yeah.
maybe such a route would allow host magic that we might, but I can't think of anything, and that's why I'm asking, I suppose.
Yeah, I mean, I think to the extent that one needs additional APIs from Wasmtime, we could add them to this world. And so then I guess my thought on that is, we're talking about plugins into Wasmtime. Wouldn't it be cool if we had a technology to allow plugins into a program? And we do. It's called Wasm. And so I think basically this is nice in the sense that you can develop without building the thing into Wasmtime itself. I can speak just personally as I was developing this GDB stub implementation. It was super nice to have like half-second rebuilds on the Wasm component rather than rebuilding Wasmtime. And there are all the safety aspects as well. So whatever. I think that if we hit any use case where we can't build something today because we need some additional capability, we should just add it to the API. That would be the answer. Yeah.
All right, we're already out of time. I will allow 2 very quick questions, so very brief. Nick, you first.
Yeah, I just wanted to say super fantastic to see the demo come together, and I'm really excited.
Thanks.
And Alex.
I would echo that. Are the LDB stuff, is that all upstream, or is that like extra patches
Yes.
for LDB?
So I checked out LDB get and built it, and that's what I was running.
Nice.
Yeah. So the only caveat is that, again, I think most distros that just build and ship LDB, like Debian's package or whatever, don't include the process WASM support. And so I think we probably should include in WASI SDK a build of LDB, but
I
that
agree.
shouldn't be hard.
And there are more questions that are in the Zulip. Folks are very excited. Please continue any additional questions you have. Just throw them in the Zulip, and folks are more than happy to get back to you on them. And with that, we are going to kick it over to Nick again for handling in Wasmtime. Let's get it. And you are muted, Nick, by the way.
All right, so I'm here to talk about compile time built-ins again. Just kidding, haha. All right, this is visible, yes?
Yes, it is.
Thanks. Yeah, so as some of you may know and some of you may not, I have been on a quest to handle out-of-memory errors in Wasmtime and make Wasmtime robust in the face of the allocator returning null when you try to malloc something. So this is going to be just kind of a update on the status of that and a bit of motivation of why we're doing it and kind of what we've learned so far, etc. So the goal is to allow embedding Wasmtime into environments where the system does not kind of overcommit memory, like Linux kind of famously will, and where the allocator will return null if there isn't any more space for your allocation. And so the goal is that when the allocator gives us null, then we are going to return a recoverable error and kind of propagate that out to the embedder, whatever the embedder's kind of like public API that it called into Wasmtime with was. And we'll do this rather than panicking or aborting, which allows them to kind of free up space and try again, or otherwise do whatever they feel is best in this scenario. So yeah, I mentioned rather than panicking or aborting because the Rust standard library, if you use that, depending on if you're using just alloc or you're using stud, is going to either panic or abort. And so by default, if you're using the standard library collections, that's what's going to happen. So the second question is kind of like, what code paths are in scope here? Is it going to be literally all of Wasmtime or just a subset? It is going to be just a subset. So I would say the boundary is not super, super well defined right now, and is mostly kind of driven by what the embedding that I work on actually requires. But basically, it's kind of all the stuff that works in no-stud builds. And so this is mostly like WASM execution. So loading and then running WASM binaries that you pre-compiled on some other system, which did, not need to deal with out-of-memory errors. And then also, you need to be able to call, WASI APIs. And so that means we also have to make WIT bindgen generated code kind of robust to handling, as well as the Wasmtime WASI IO crate, which is sort of how you implement WASI in no-stud builds if you don't want to use kind of Wasmtime's default implementations. Eventually, we're going to have to get the component models kind of async concurrency runtime handling out of memory as well. That's going to be a bit of a tricky one. We'll talk more about that later. And then specifically, I'd like to call out that like getting all of crane left to handle is not a goal here. And compiling WASM in general is not a goal. It's really just running pre-compiled WASM. So our high-level plan was kind of basically to start with defining our own Wasmtime error type. So we used to use anyhow error. Now we use Wasmtime error. And it's API compatible. They're basically the same thing. And the migration across the version of Wasmtime that did that switch should hopefully have been pretty straightforward for people. But Wasmtime error also has kind of an out-of-memory variant. And it also handles allocation failure internally. And so when we have that in place, now we can actually go about kind of returning out-of-memory errors in various places. And so the big thing to do here is like, when are you allocating, is because you have a collection. You need to put stuff somewhere, right? And so we can't use the standard library collections directly because, as I mentioned before, they're going to either panic or abort on and so what we're doing is we're defining our own vec type, for example, where vec push, instead of not returning any value, returns a result of either, unit, or, hey, out of memory error, we would have had to resize the vector, but trying to resize it resulted in allocation failure. And then we also need a test harness for exercising handling. We'll get more into this in a little bit later. And so all those things are done and landed. And so what's basically in progress now is just going through all the stuff that we need in Wasmtime and, going module by module, function by function, and switching things over to using the handling vecs, adding a test for that code path, and just, going until that passes, and then we land that, etc. And then also, the plan is to start fuzzing the handling and injecting an on a random allocation or whatever, and making sure that Wasmtime doesn't crash, that we correctly report the error, etc. So to talk a little bit about the error infrastructure. So this is the Wasmtime error submodule, which provides basically an identical API to Anyhow. And then a bunch of that stuff is also re-exported at the top level of Wasmtime, just because you use it so much, like error, result, etc. And then there's also this out-of-memory error type, which the constructor takes kind of the size of the allocation that failed, and then you can get that later on via this requested allocation size getter, if you want to like print, hey, we tried to allocate this much, but it failed. And it was really important to make the size of this stuff as small as possible, and able to take advantage of Rust's niche optimizations, like type niche optimizations. And so we return, results all over the place. In particular, like result unit is probably the most common. And we want to make sure that that fits in one word, so that we don't have to allocate like, return buffers at the machine level ABI or anything like that, right? We can just use registers. And so the way we do that is, the struct error is a wrapper around this thing that's either an out-of-memory error or a dynamic like error, like any kind of error, right? Similar to like a din trait object. And so that's represented with a non-null pointer. The non-null is important because that's what allows the result discriminant to fit into the null bit, and determine whether we're in the OK or the error. And then or din error is, so it's a bit packed equivalent of either an out-of-memory error or a boxed in error. And the bit packing is when the low bit is set, it's out of memory, and otherwise it's a din error. And this is because din error has higher alignment than out of memory does. And then so out of memory, low bits always set, other bits are the allocation size. So, it's represented as this like non-null pointer, but it's not actually a pointer to anything. We never dereference it or anything like that. So star mute din error is like star mute din core error, like a din trait object pointer. But a trait object pointer is a fat pointer. It's a pointer to the actual object, and then it's a second pointer to that object's vtable. And so that's two pointers, that's too big, and it breaks our size goals here. And so din error is essentially a custom version of that moves that vtable kind of more in like the C++ style of putting the vtable into the object itself. And so we have these kind of two parallel structures, din error and concrete error, which have the same exact kind of prefix of fields, and they're rec's so that they're always at the same location. But then din error has some trailing error, but we don't know what it is. And so we're never dealing with these things by value. We're always dealing with them behind some kind of pointer or reference or whatever. Whereas the concrete error has the actual error. And so we'll cast a concrete error to a din error. And so then all the stuff you need to ask about an error, like you can ask, is it this kind of type? Like, can I dynamically downcast it or whatever? That's going to call through the vtable. And then there's a trait error ext that is ultimately sort of like what we're calling. So everything that is in this like concrete error implements error ext. And so the way we get there is the vtable has this unsafe function that takes a din error, and then what it does is it has, when you create the vtable for a particular type, we get monomorphized versions of all these functions for that particular type that cast the din error unsafely to a concrete error of that particular type, and then call the trait implementation. And so it's, the unsafe bit is like making sure we have the right functions in the right places. Yeah, handling collections. We have a bunch of them landed in tree. We have vec, string, hash map, etc. You can look at all of that. We will need B-tree maps and B-tree sets, but we have not implemented them yet. And then basically whatever else we run into while adding tests. Haven't seen too much of anything else, but this is where we are so far. All of this stuff is defined in two places, either crates core source alloc whatever, or crates environ source collections whatever. Generally things are in crates environ source collections or whatever, but sometimes there's like an internal dep that is used both in CraneLift and Wasmtime, and that's the stuff that ends up kind of in core. You can always use them via Wasmtime environ collections because Wasmtime environ collections re-exports everything from the core crate. And then generally what we do is we don't implement the collection ourselves from scratch as much as possible. Instead, we're kind of wrapping over the standard libraries versions of these things. So for vec, we define a vec-t, but then the inner is just the standard library's vec-t, because the standard library provides an API try reserve. So when we reserve, we ask for whatever additional amount of space you need, and then we return a result based on that. And then instead of calling the inner regular reserve, which is going to panic or abort on we call try reserve, which does return an error. And then we turn that into an out of memory error and return that. And then push in kind of the standard library, it doesn't return anything. It's going to panic or abort on What we do is we will return a result of either a unit or out of memory. We'll do that reserve ahead of time. And then if that succeeds, we know we have space for the item, and then we push and it's okay. So by doing this kind of stuff, we don't have to actually implement all of the unsafe data structure and pointer manipulation and buffer ownership ourselves. Hash-based collections are a bit tricky though, because as far as I can tell, we don't really have a hard guarantee that if we do a self-insert after a successful reserve of one more space, that's never going to allocate. Because if there's a bunch of weird insertions that all end up colliding, right, that could require reallocating to redistribute all of the things. Been ignoring it so far. It hasn't been a problem in our tests or fuzzing or anything like that at this point. And if we do run into that, then we're going to have a bunch of questions that we're going to have to ask ourselves. And I do expect we're going to run into this eventually, but I would like to make progress on the low-hanging fruit while I can. So I'm kicking this down the road or whatever. Additionally, an unfortunate bit is that our hash-based collections don't expose the entry API. And this is because the inner std types don't expose any kind of like try insert. They only expose try reserve. And so we can't we don't have a way to kind of like wrap the entry API from std. and do the like reserve before insert thing that we do. B-tree based collections are also going to be a little tricky because unlike vex and hash maps, the B-tree types don't have any reserve or try reserve, and they also don't have try insert or whatever. So we can't actually just build a new type wrapper around them. But we really lucked out because it turns out we have a B-tree implementation in the Wasmtime repository already. And that's CraneLift bforest, and it's kind of arena based, which means that all of the allocation happens in that arena, and the arena is ultimately a vec at the bottom, so it's pretty easy to add a fallible reserve and everything, and add fallible allocation to this B tree. So we really lucked out there. We also added a bunch of various like try traits that return a out of memory error on allocation failure, but otherwise are basically the same as traits from core, alloc, or stud in the Rust standard library. So Rust provides clone, we have try clone. It provides collect, we have try collect, etc. And then additionally, our SERDI serialization, deserialization implementations need to handle luckily, that didn't require moving away from SERDI or anything like that, because when you're deserializing, which is when you're going to be doing the allocation, the error type that you return is a generic type parameter, but it's bounded by this like SERDI, deserialize error trait. One of its constructors that it exposes is custom, and so we can pass through there, and it's not a problem. A little bit of a side on dependencies. Generally, they're a huge pain to use in code that must handle because they don't use our handling collections. They use the standard library collections, which will allocate without returning an out-of-memory result, that will panic or abort on failure. In general, they don't implement try clone. They implement regular clone, and they will allocate inside regular clone. And so, unfortunately, we're really swimming against the Rust ecosystem's current here. I mean, you can see because we're implementing our own, try version of all the really base level traits, we're really kind of like forking off from the ecosystem at the very standard library level. So it's not great. We could potentially try and, if we find other people who have similar use cases as us, we could try and create a shared sort of like try stud or something, and build like an ecosystem of people that are handling out of memory errors, perhaps. But luckily, our core WASM execution code paths are basically free of dependencies for the most part. And so this doesn't crop up too much in all the code that we actually care about handling out of memory in. As far as testing this stuff goes, this is very inspired by SpiderMonkey's, I forget what it's called, but their testing infrastructure. So we have a custom global allocator, and this global allocator will artificially inject out-of-memory errors on a test. So like you give a test function, and it's going to run that function multiple times. And what it's going to do is it's going to inject on the first allocation that it makes, and then check that it properly handled and it returned an out-of-memory error correctly and everything. And then it's going to run that function again. And but this time it's going to let the first allocation pass, and it's going to inject on the second allocation, right? And then it's going to do the same thing on the third and the fourth, etc., until the test completes and returns, okay, because all of the allocations succeeded. So small requirement is that tests need to be single-threaded here. We could lift that if we really needed to, but it hasn't been a problem so far. And yeah, as I mentioned, it's exhaustive for now. It does the first, then second, then third, then fourth allocation, etc. But the plan is when we get to the fuzzing situation is to extend this existing kind of test infrastructure with an inexhaustive and kind of pseudo-random mode for fuzzing. So fuzzing will say, instead of exhaustively doing this function, just like do like the ith one, this random one, which is necessary because the fuzzing can't time out or whatever. All of these tests live at crates fuzzing tests .rs. The test infrastructure is at crates fuzzing source .rs if you need to see that. This is basically what one of the tests look like. Import the stuff. You have to set the special global allocator, and then you use this test builder and run a test. And you can create a config and create an engine, and it will make sure that all of the allocations that happen inside of that closure are properly handling so where are we so far? So you can create, like what code paths actually handle so creating a config, an engine, and a store all handle as far as running and loading core WASM modules, you can create a linker and define a function in the linker, or multiple functions in the linker. This whip, deserializing a precompiled WASM module, actually landed yesterday, so that's a checkbox. So you can deserialize a precompiled module, and we handle there. So next up is going to be instantiating that WASM module, and then after that, executing the WASM module. And then got to do all that same stuff again for components. And then got to handle, Wasmtime WASI IO and whip bind gen so that we can start, covering WASI APIs. And then at some point, we're going to have to deal with the component model async runtime. And this one does really depend on the futures crate, at least right now. And the futures unordered kind of combinator within, which is like almost like a little mini async executor. I suspect the futures crate people don't want to add, fallible allocation try stuff to all their things because it's kind of gnarly and I don't know. So I suspect what we're going to have to do is cut down as much as possible on stuff that we use and then fork our own versions. But this is still up in the air and it's going to be a little while before we have to cross this bridge. So if people have opinions here, please talk to me, let me know. And then ultimately the goal is for the Wasmtime crate itself to not have extern crate alloc anymore at all. And that doesn't mean that it can't ultimately link against alloc. So for those that don't know, alloc is the crate, the part of the Rust standard library that depends on a malloc-free implementation. And so we want to not depend on that directly, and instead only depend on our internal crates, which can link against that, but then expose the new type collections that return out of memory errors and stuff, right? So that when you're in Wasmtime, you literally cannot use something that's going to do the wrong thing. And I suspect that when we, flip that switch and remove the external crate alloc, there's going to be a long tail of stuff that is just, we didn't see it in the earlier processes, and we're going to have to go fix it at that point in time. So if this sounds like interesting work to you, I think at this point it is pretty parallelizable. And so if you want to help out, you can. Basically, all you have to do is choose a public API from the Wasmtime crate where it makes sense that we want to handle there, right? So basically not compilation or whatever. So for example, creating a new resource on the host. And then go into the test file and add a new test that calls that API. And then run that test with logging for Wasmtime fuzzing enabled. And so what that's going to do is in the test, whenever we inject an we log first the backtrace of where the allocation is happening, right? And so you basically just run the test with the logging, and then you see what the last backtrace was, and that's the place where you aren't handling because you'll crash right after that allocation. And then you basically just need to switch that over to using handling collections or whatever as necessary and propagate the out of memory as necessary. And then just run the test again. And pardon me. And just keep doing that until the test passes. and then now you can commit everything and send the PR. So yeah, that's everything that I had. And do people have questions or anything?
Yeah, there's quite a bit of activity in the Zulip. Ryan expresses support for tests. Yash says, if you want, I can put you in touch with the Rest for Linux folks. They have very similar fallible allocation needs as Wasmtime and might be interested in collaborating on something like Tristed.
That would be really, really interesting to talk with them. At minimum to kind of share experiences, but yeah, it'd be really cool to see where that goes.
Joel says, well, Joel edited his message. Joel says,
Do you want me to just say it?
yeah, go ahead, Joel.
Sorry. Yeah, I edited the message because I seem to recall last time I looked at futures unordered that it was mainly just backed by a hash map or a hash set. Now taking a look just now, it looks like there's more to it than that. Perhaps my suggestion stands, which is that we could look at forking it and creating our own OOM safe version as a start, and then maybe think about upstreaming as a second step.
Yeah.
Excellent. Yash also says, if y'all switch to futures concurrency, that he'd be happy to add support for fallible allocation behind a flag, and the equivalent to futures unordered is future group.
Okay. Yeah, I'm not super familiar with future concurrency, but let's talk. If it's gonna make our lives easier, which it sounds like maybe, it sounds like it's worth investigating.
Bailey says, I wonder how much work the Wasmtime WASI IO step is, and if it's worth considering scoping to just P3.
Well,
I actually offered an answer to that. Sorry to interrupt, Nick. Which is, I mean, first off, Nick, you're doing a really great job on this, and this is a ton of work. So thank you. I think doing Wasmtime WASI IO is relatively small compared to many of the other things you did. And also it just happens that for our embeddings, we need P2.
Yeah. Joel, I see you have your hand up.
Yeah, it's a new topic. So if we're done with that one,
Yeah, go ahead.
Maybe we are. So I was just thinking in terms of kind of the big picture here with P3 and whatnot, there is a lot of code in kind of concurrent.rs and futures and streams.rs and whatnot. I can't think offhand how much more besides the futures unordered, which is indeed the core of it. But I'm wondering if part of the strategy here might be kind of taking a cue from Chris's presentation to kind of push some stuff down into components, potentially part of the component model async implementation could itself be a component. And this actually alludes back to Luke's presentation yesterday, where he was talking about this lower component idea, and part of that, which I'm planning to write an RFC for, would be this idea that you could take create a component lowering thing that could embed code that does the P3, the component model async stuff, bookkeeping and whatnot, task juggling in the component itself, and thus, this lowered component could then run on a relatively simple core WASM runtime. And I'm wondering if we could kind of take a step towards that. I don't know if you've thought about that, or if what you think of that.
I haven't thought about it in the context of handling. I am, in general, a fan of self-hosting, as you might guess. We've talked about this before in terms of part of the Wasmtime's GC implementation. So right now, our free list implementation is not super great. Don't need to get into details there. But one thing we identified could work out really well would be essentially compiling dlmalloc to WASM, and then using that as our free list implementation and sort of like self-hosting a lot of the GC. So yeah, there's a lot of stuff that's sort of interested in this space, and it would be great to like push towards that wherever we can.
All right. Well, with that, folks, it's time for a break. So we will meet back here at 10 a.m. Pacific time. Um, but of course, feel free to hang out here, vibe out, maybe even have sparkling water beverage. Maybe, I don't know. But with that, see you folks in 14 minutes.
One fun thing is Ryan has a new blog post on the Mozilla Hacks blog, hacks.mozilla.org. Maybe I'll put it in the chat.
I actually just put it in the chat.
Hey!
Making WebAssembly a first-class language on the web. Oh, baby. David, how's the summit treating you?
Great.
Excellent.
And you, nice, great job as host, by the way, Oscar. So
This WebAssembly stuff can be a little
I,
heavy, and so just trying to keep the mood a little bit light as we
well,
navigate
I think
through
you're
it.
also kind of, like letting the inner Oscar out here on some of the, be still my heart stuff. So yeah.
Oh, yes.
It's nice to see people get excited about debugging.
I mean, I think it's incredibly exciting. I mean, because this is stuff, as WASM nerds, we've just dreamed of. Because, especially for the people, especially that are here in the Plumber Summit, we've been in the situations where we wish we had something like this. And instead, because for a lot of us, it's like, is there a bug in my guest code? I don't know. Is
Well, I
there a
mean, yeah,
bug?
there's some of us that have been around programming long enough that we didn't even have debuggers. So, right. I mean, printf was your debugger. Good luck to you. So
Still a very powerful debugger. All right.
cool. Yeah.
No
Yeah.
shame on
Many
printf.
hours in ADB or whatever before, we had stuff to work with. So it's great.
Yeah, a big reason why I wanted to work on this project was that in the 2 years I was working on Weevil and making JS fast, there are so many times when I had bad bytecode and I was like, what the fuck is going on? Uh, and staring at like 10 million line outputs from WASM to WAT. So
Yeah. Yeah. Well, I could tell when you were doing the, describing the use cases there, Chris. I mean, the last one you came to was very much like that was the use case, right? So it's, right. Yeah.
I do so I showed in the chat that you can single step at the WASM bytecode level now. I do want to see if we can push a little bit LODB. Like you can't print WASM locals, you can't print WASM globals or the operand stack. So it'd be cool to really build out like a WASM native debugger capability, like what browser dev tools have. I
That
feel
would be
like that's
great.
a big vision. That'd be cool.
Yep.
Yeah. I mean, it shouldn't be too hard to build a little TUI, right?
At debug.com. Yeah.
Yeah. Famous last words.
I'm actually sort of surprised. What happens in LODB if you type like info locals? I would assume that it would something would say here's all locals, and you could probably inject all the WASM stuff there in theory, but I'm not.
It will show you source level locals per the dwarf. It won't show you like WASM locals. It understands the WASM locals when it parses the dwarf, and the dwarf says, "Oh, it's local 3, whatever." But yeah, there's only
Well,
one register in the machine definition in GDB, which is PC. So
I guess yeah. I think what I'm thinking of is more like inter registers, and you kind of need a variable number of registers per frame with different types per frame, which I suspect GDB is not a huge fan of.
yeah,
Also, like different kinds of registers, like globals versus locals versus operand stack.
Could you pretend WAT was the source language? So take the WASM, render WAT, generate its source debug info from as if WAT was the source language, and then debug that.
you could in the same way you can use LODB to debug assembly on native hosts today. You can, and you can single step. The thing that you can't do, well, so it's a .s, which is LLVM's interpretation of WAT, right, which is linearized. The thing you can't do is, yeah, as above, you can't print locals or whatever. So
Wait, so the disassembly you're showing is actually, are you feeding WASM bytecode to LLDB and it's disassembling it with LLVM?
So the
Oh.
way the protocol works is there's a synthesized address space that includes the source bytecode for all the WASMs. So that's why you got that PR a few days ago. Uh, and LLB will actually use the protocol to read the memory over the wire and get the WASM and disassemble it.
It's kind of wild.
It's pretty cool.
Out of curiosity, what version of LLDB has all the WASM stuff built in?
So I'm using a Git checkout from 4 days ago. The main PRs started in 2020. So Jonas DeFiglier, whose PR we commented on at one point, I think last summer, has been doing this for a few years now at Apple. The older versions, so like my Debian has LLDB 19, and without the WASM plugin, it does still do some things actually. It will still like single step. It just can't read locals and globals, so you can't see like the source level stuff. So I think the latest LVM release does have all of this. So probably like the next WASI SDK release we can see about including this. But
So, Chris, your top priority is working on GC support in the debugging, right?
oh boy, that would be cool. Yeah,
I want to see my structs, Chris. How can I see my structs?
that would be cool. I'll leave it at the neutral value judgment of that would be cool.
All right. Which actually, while we're just shooting the shit here, should we get rid of arrays in WASM GC? Should we just should we just have structs?
What, just like cons linked lists or something?
Yeah, you
Like
know what I mean? Like,
list
So
pattern right, all
struct
those
with
use
like a lem 0, a lem 1, a lem 2.
yeah.
oh, actually, this is very off topic, but Nick, this is something I wanted to pick your brain on. So we have the proposals in Core WASM to like find some way to like be able to like load like F32s or I64s or whatever from like list U8 or array U8, I guess. Array I8 in WASM GC. What if in a type system we just straight up allowed you to cast that to an array of like F32 or like I64? You're muted.
Cast the memory.
Like if you had
Or
an array of like I8, like could you just cast that to an array of like F32 so that way you could use all the like load instructions and stuff? Because it's like there's nothing wrong with that fundamentally, but do we break the entire WebAssembly type system by allowing that?
I'm sure there's like some issue there.
I will call Andreas right now.
Yeah. Yeah, I'm sure it's some type system issue, probably.
Wouldn't alignment definitely be an issue in the sense of an array of U8 might not be aligned?
Well, I mean, you could just like
Alex, I don't
force
like your
alignment, right?
counterexamples, okay?
Yeah. I mean, I guess like you would effectively have to make them all subtypes of themselves or something, or
No, but what if we didn't do that? What if we just said, hey, you can
well,
cast
you would
this
have to,
as
because if you turned like one into the other, then you could pass the other into some function that takes that other type, right? And so like that's sort of like what
well, if it's a
subtyping
real subtype,
allows.
but like, what if it's not a real subtype? Like, I'm not even saying it should be a real subtype. Like, we just straight up let you cast it. Or alternatively, if we didn't want to actually ruin the WASM type system, we could have a actual instruction that let you convert them. which might actually be an easier way to go about than, you know, adding all these extra new instructions. So just one instruction that lets you convert it. And then like if you wanted to trap on alignment or something, like well, I wouldn't do that, but like
What if other
something.
stuff is still holding references to it as the old type?
Y'all keep hitting me with counterexamples and like this is glorious break time.
Yeah.
Oscar, what you want is unsafe transmute. It's there already.
Oh, it's not there in WASM.
Not in pure WASM.
Oh, like pure.
Like I'm saying, like when I'm ripping some WAT straight off the dome, you know.
I think what you could do, I don't know if this is better than just introducing the instructions or adding the immediate to allow the memory instructions to work on various types of arrays or whatever. But you could have like like views, like slice views or whatever.
Yeah.
Right? And then I think that would be something that you could design to make it work in all these situations. But yeah.
What did I do on stage? That sounds like I had an embarrassing accident. I'll never forget.
No, it was awesome. It was awesome.
That's even more ominous. But thank you, Bailey.
You don't remember when you got the Python interpreter going on stage? You're just like, all right, so I had to write this WAT to make this work. It's like
but
4 years ago.
So WASM people, is that exciting? Like everybody's just, you know, writing some WAT, right?
And in those days, yes, and yet we had so many people that have probably only written Java and Go in their lives in the audience. And they were like, you can just do that?
Yeah, no, I mean, well, if you're a WASM nerd and you just want to just get your hands dirty, WAT is very writable and very readable. Also, I mean, I grew up with S expressions, and maybe not everyone's a fan, but you know, genuinely, it's very easy to read and write. Whether you want to just do the like WASM stack machine type and just like write all your instructions in order, or you want to nest them, like you know, you can do both types. So like whatever flavor of writing code you like will work with WAT, which is really nice. And it's like a good way to just like demystify a lot of WASM. And then you can, you know, get into trying to understand what all the SIMD instructions do. And that's when you start losing your mind. We have syntax and sorry.
I mean, I'm gonna do it again because I brought it up yesterday. Have you tried using an LLM to write WAT? I've had awesome success. It's actually really good at it, and that's wild. It makes sense. I get why, but also,
I mean, like it's pretty basic. You only have 4 types. Yeah. Well, okay, we have way more than 4 types now, but like it's not terribly crazy.
By the way, MDN recently added a lot of docs for like writing WAT.
Do you know who put that in?
Sorry?
Do you know who wrote those docs? Just wanted to give them a shout.
Yeah, it's not a WebAssembly person, actually. It's one of their technical writers. They asked me to.
Cool.
I know.
Yeah, it's funny because I find writing WATs to be pretty easy, but when it comes to like component WATs, where it's just like, okay, we've ascended. It's like now I have like all these core modules and then instances of them, and like that's when, like to me anyway, that's where it starts getting a little crazy. But it looks like we are right on time to come off of our break. So I hope all of you are rejuvenated and well hydrated. With this, we're going to get into some amazing lightning talks. First up, we've got Pat Hickey with a follow-on for the February 24th security disclosures. Pat, you want to kick it off? You're muted if you're trying to speak to us.
Hi. Hi, everyone. Thanks, everyone, for being here, and thanks to all the great talks so far. So y'all might have seen earlier this week on Tuesday, we released actually 3 Wasmtime security advisories. Say 2 are pretty minor, one of them's a big deal. This is about work that has to follow on from that. So the advisory itself, I'm not going to read it to you here. It's very well written. You should go and read it. This guest control resource exhaustion of WASI implementations is the title. What does that mean? It means that if the guest does something, it can cause a WASI implementation to allocate a lot of memory or otherwise do things to exhaust resources in the process, right? And we didn't have control over that prior to this patch. That's frankly an oversight. It's been in Wasmtime since day zero, or since the very first time WASI was ever implemented, essentially. So some credit on this work. First off, we actually found out about this because a brand new contributor reported a memory leak and sent in a patch for that leak. It happened to be in the Wasmtime WASI's preview 1 impl. So really cool that mbund did that report for us, and they sent in a totally good patch for the one particular issue they found. Alex was the one to field or triage this because he wakes up before us West Coast people, and he does way too much work anyway. He took a look at it and was like, "Oh yeah, this is a legit bug, but also this is just one little piece where we're allocating and a large amount of memory and happen to be leaking some of it. That's controlled by the guest." So Alex kind of took it and took a look at this and said, yeah, we should fix this whole category of issue rather than play whack-a-mole with this. And that, of course, the next security advisory fixes the next little one and so on. So thank you to Alex for doing most of the investigation remediation. I was able to help out a bit. Alex was preparing a different talk, so I offered to give this lightning talk on this while it's timely. Okay, so what did we do, or what did we find that the guest can consume host memory? By the way, this is all assuming the component model, and it happens to be that the preview 1 implementation gets implemented in terms of the preview 2 implementation internally, so kind of all applies there. Let's not talk too much about the preview 1 stuff because it kind of doesn't matter. It just kind of falls out. Anyway, okay, so by creating component model resources, right? If the host provides a vector like, for example, opening files, right? Every time you open a file, it creates a new component model resource for that file. If you were to open the same file in a loop forever, you would eventually, get to the 2 to the 32 index space before you trap. And because there's more than 1 byte, you'd be able to consume many gigabytes of host memory if you were to just sit there and open a file in a loop, is the short answer. So now there's a new limit on that. Of course, all of these constructors, they're not fallible, right? We don't have a way to return or something like that, like all that work Nick was doing across the component model boundary, right? So now if you hit the limit, it traps. And in general, that's going to be the theme here as you go down the page. There's lots of other things in WASM where if you reach a limit, you trap the so-called implementation limits that all the web VMs have, and Wasmtime follows. But those tend to be on things that you can analyze about a module. This is things that happen at runtime. So that's the difference here. Okay, so we said we did create a resource, but now let's look at more specific things, right? Any import function that accepts either a list or a string, which is to say lots of useful ones accept lists or strings. Those are very useful things. If they accept really large, you can in the guest give them a really large list or a really large string. So when you pass that to Wasmtime, what Wasmtime will do is allocate a vec or a capital S string, which is under the hood of vec, in the host, and copy all that information out from the guest to the host. So again, that was only bounded by the size of a linear memory previously. And so now we've got a limit on the total size of lists you're allowed to, lists and strings. You're allowed to allocate in the host across a single import function call. So if for whatever reason you accept 3 lists through a call, or worst case would be a list of lists, which will allow you to do quadratic, right? You'll now, each time you allocate something in the host, it'll count against a fuel limit. When you reach that fuel limit, Wasmtime, rather than continuing to allocate things in the host, will instead just trap that whole import function. Okay, and then so those two are actually really easy. We were able to take care of those with a limit that takes care of all of them. Then there's the hard case, and that is some particular import functions. They take an argument, and it happens to be that calls an allocation that's not straightforward from the types, right? So the first example is stream or file read, right? When you say read, you say, how much do I want? The size argument, right? It's a U32. And Wasmtime will dutifully allocate a bytes mute, which essentially a vec of U8 of that size, and then do a read into it, and then pass the ownership of that over to the guest. So that is, again, a way where an integer in the argument can make a big allocation in the host, right? So if you were to pass 2 to 32 there, and you were on a system that didn't overcommit, or you were near the limit or something, that could you. Or at very least, it could contribute to the memory pressure of the system and so on. So just so happened we already had a maximum read size allowed by the spec, and you could always read less than you were asked for. So it's cool. Like, we just capped that one, right? We were able to look at that case and say, all right, well, you asked for 4 gigabytes of read, but we're only going to give you 64 megs at a time. And then in user land, your program will gracefully, then go and read the rest of what it needed in chunks. So that one's not in red because that one's not that bad. One that we encountered that we didn't have an escape hash like that was get random bytes, right? In the random interface, you say, I want this many random bytes, and the function is just U32 argument 2, list of U8 result, right? So there's no fallible. There's no way of saying, oh, I'm giving you less than that number of bytes, or you asked for too many. So now if you ask for too many random bytes, it just traps. That was a choice we had to make there that would break user land the least. It's not a choice we liked making. But there's a new limit on that, right? And then the last one was HTTP fields. This is in the WASI HTTP proposal. When you make fields, is just the synonym for headers and trailers because they're the same structure. It basically gives you a way of saying, okay, here's an arbitrary key value pair, the value being a vec of bytes, right? Just unbounded in size. And you have to tack that on and append. There's the .append method, right? Tack that on and append that to this resource. The resource has to own forever. So now we say, okay, you're only allowed to allocate up to 32K for that stuff total. There's a new limit, right? It ends up being that for anything that's web interoperable, more than 8K of headers tends to stop at various proxies by default. That one probably doesn't break as many well-meaning programs, is the point. By the way, as a bonus, we also found another security advisory where the HTTP creates header map thing would panic because we made a bug. HTTP create probably didn't have the best API design anybody's ever seen. So there's like a less consequential advisory, or sorry, a less interesting advisory that is consequential that was fixed as well in the patches that just came out on Tuesday. So I want to like the part of this talk of like, what do we do next? I just said what we did. And what we did was security mitigations. We did not come up with long-term solutions to the problem, this category of problem that we uncovered here that we didn't really consider well enough prior to this incident. And by we, I mean, me and many other people who worked on this code for years. This was just an oversight. But, the consequence here is we broke user land. That's the thing you're not supposed to do, right? The one I worry about most is random, right? Because it's just like, oh, libc will just pass that through. There's well-meaning programs that might have wanted a whole bunch of randomness. And how do we know that we didn't just cause a valid program to trap? The number of resources is similar to the file limit in a Unix process, where it's like, okay, well, now there's potentially well-meaning programs that trap. Luckily, there's not a lot of WASI programs out there that are doing super opening a whole lot of files, just kind of by design. But this is unfortunate, is my point. Also, we did so unilaterally. We broke these programs unilaterally. Like Alex and I we're in a security issue. We couldn't make this a WASI issue and talk about it for a month or two and collect lots of community input before we did this. We had to get a patch out within a week, so we had to make these decisions within days. So this is to say, what we chose on a mitigation timeline doesn't mean now we can't get community input of were these the right choices? We can still we broke userland, but we can change the way we broke it over time because we did so for security mitigation. We weren't following a standard by breaking userland here. And I think the biggest thing in my mind that's a problem about this is, when I say we set limits, what we did was we chose default limits in Wasmtime that seem to make sense to us. And there's always a knob, whether that's you're an embedder, they're on WASI Context Builder, WASI HTTP context. There's a knob to change the limits, or those turn into Wasmtime CLI flags if you're using Wasmtime on the CLI. So the idea is okay, well, you could change these limits, right? We made a knob, but the guest can't know what you chose as your limits, and it's gonna trap, right? So not only can we make WASI libc and dubstud and other places respect the default limits, which I haven't done yet because of this we did so unilaterally thing where we want to kind of let this marinate a bit to find out what the long-term issue is or long-term solution is here. If those limits change, there's no way to discover them. So that's undesirable. It might have to always choose to do that in some cases, but that's undesirable. The real call to action for all of you on this call or watching is, Alex and I patched this in Wasmtime WASI and Wasmtime WASI HTTP and the Wasmtime CLI that's built on top of those. If you are not just using those implementations and pulling in the patches on them, you probably have to go and do that special case discovery, the stuff where we found file reads, random, and HTTP fields, right? You have to go through your code base and audit it. If you have interfaces that are not part of those, CLI world and proxy world interfaces, you have to go and audit those and the implementations of them and discover whether you're susceptible to this. So that's probably the most dissatisfying thing about this whole process to me is we uncovered a new category of things we hadn't really thought about. And it's not just us. I mean, Wasmtime, we did our job with the Wasmtime project and its scope, providing security fixes for this. But if you're an embedder of Wasmtime, you may and probably have more work you have to do. So this is kind of a PSA to please go do that. And finally, what do we do with the standards? Like I said, we did this all without community input. This is a big amorphous design space that we have definitely not explored. So the first step is, and this part of what this lightning talk is to kick off, is socialize some actual plans, figure out in the standards, figure it out in the Wasmtime repo if necessary, of what a long-term solution to this looks like. And that can include questions like, does the component model spec take on the resource and lifting fuel implementation limits? It should probably describe those. Does it specify what the limits are? I don't know. There's a lot of open questions there, and this talk is not about trying to answer any of them. Of course, the WASI P1, the WASI P2 specs are done. We're not going to make breaking changes to the functions that we had to change where they might trap. So we need to document if we agree on the way they should behave, that they may trap in those cases, if we settle on that. And finally, the WASI P3 spec is not out yet where we can't make breaking changes. So can we make any design changes to WASI P3 now before it's out that will save us from having to have unfortunate trapping behavior that's only found in the spec text. Or if we do have to do that, we can at least settle on it before the spec goes out. So I know that release is coming soon, and a lot of people are counting on that. And I totally get, having been the release manager of this before, how tricky it is to do things at the last minute. But I just want to call that out as a to-do, to talk and think more about it. So anyway, Alex filed issues on the WASI repo, 888, 889, and 890 to go and talk more about these. That is all from my talk.
All right, thank you so much, Pat. Folks have questions, please put them in the Zulip, and folks will answer them async. With that, Chen, with a tool and library for WIT component virtualization.
Yeah, sure. Let me share my screen. Yeah, so I'm going to talk about a tool we are building for instrumentation for Watson component. So traditionally, if you want to instrument your program, you usually have two ways. Either you do a binary rewriting of your code and then insert some instructions in there, or you can do it on the host side where when it calls to the host and you have some runtime hooks that does some monitoring, or a mixture of both. Basically, you call a host function and then you does the monitoring logic in the host side as a host function. But what's interesting here is that component model seems to give us a third way of doing instrumentation, which is kind of like a proxy or a virtualized component. And the idea is quite simple. Like if we look at this calculator component, which imports adder and exports eval function, and the way we can instrument this component is by building two more components, which we kind of call a burger wrapping. So kind of the upper bound is exporting exactly the same interface this calculator is expecting, and we can import the original interface in the upper bound here. And then here's like a simple Rust implementation that basically calls into the import add, and then you can add arbitrary logics in here. So the upper bound is responsible for instrumenting all the import functions, and the bottom bound is instrumenting the export functions. So the pros to this approach is that you are not changing your user code at all. All we do is we are adding some new component and then whack them together. And then from the runtime's perspective, the whacked component looks exactly the same as the original component if you look at the WIT interface. So this means if you're doing instrumentation, then for the host runtime, there's nothing to change. You can run it basically in any host runtime that originally supports this. You don't need any change. And also another nice thing is that you are doing this in a separate component. So that means you can implement all the tracing logic in a high-level language like Rust or anything that supports component model. And then it's a separate memory, so you don't need to mingle your ARM user memory and worry about corrupting the user space. And also, since we are tracing at the component level, so everything can be expressed in weight, like you even using the wave syntax to do some logging, and it's quite human readable and even human writable. So imagine that you can even write some test cases using weight and then interact with this instrumented component. And another benefit is that if you're doing this on the host side, then we are kind of fixing the APIs that we can trace. Only the host calls get traced. But if you're doing this on the guest side, then we are only going to trace APIs that matters to this particular user. Maybe we are having some other wrappings around this component that it's private and we don't want to expose those communications, and we can do it on the guest side. And then the cons to this approach is, one is we are doing this on the weight level, so you can't really instrument things at the instruction level. But on the other hand, it's just a complementary approach. You can still do the binary rewriting as you do before. If you want to instrument at the instruction level, this just provides a new way of doing instrumentation, or more lightweight instrumentation, if all you care is at the component boundary. And you can do this all today by writing new component by hand and then whack them together without needing a tool. But the problem is that you have to implement all these interfaces yourself. And if you're doing some big weight file like a WASI interface, then there's a lot of code to write. And especially if you have resources, and then that basically needs to replicate this resource from the host side resource table into the guest side resource table. So there's a lot of the stubborn code you need to write, which is exactly why we're building a tool to make it transparent and automatic. So all you need to do is to provide me the Wasm file, and then we can generate all this component for you and then whack it together. So now I'm going to give a demo. Let me try to share my. Okay, so we built this CLI tool that basically takes the Wasm file that's used the calculator as an example, and one of the mode we implemented is like a fuzzing. It's a fuzzer, so it basically takes the adder function and returns some random values. So here is trying to build the instrumented component. It basically reads the weight file and then generate a appropriate stubbing for them. And then finally we get the compose Wasm file. And then we can just take this file and then run it in regular Wasmtime without host side support. And then you can see we are making a bunch of evoke calls. And then for the import, we are just returning a random value. So at least you can run this in a platform using fuzzing. Another mode we are implementing is record and replay on the guest side. So let's say I have a Rust function that implements HTTP things on with some Fastly SDK, and we can just instrument it, and then I can run it on the original runtime it's supposed to run. Like I can take this composed Wasm, and then Viceroy here is just a Wasmtime plus some host core implementation. So I get up a HTTP server, and then I do a curl. So I get a website as before, and then I also, in addition to that, I get a trace of the whole host calls the system is making. Like I'm taking some handle and then like a request handle and pullable handle, and then do something about it. Everything is recorded here. And then with this trace, I can take the same binary, but instrument it as a replay mode. And what's interesting about this replay mode is that now everything is closed. We have the trace, so we actually don't need the original host runtime. We can just take this file and run it in the regular Wasmtime without any host side support. And we're supplying this trace to do the replay. So we can see everything gets replicated without the host side support. And since this is using Wave as a syntax, so it's very human readable and even writable. Like I can take this random bytes and then change the trace a little bit. Maybe just changing a number here. And then I can do another replay, and this should go through because my code doesn't really depends on the random bytes that's going to be implemented here. But instead, if I'm adding a new number, then that should fail. So then I get a crash because I'm asking for 16, but you are returning a 17 number here. So let me get this back. Now it should work. And then another interesting thing is with this trace, I don't need to replay exactly the same binary even. I can go back and change my original code and then add something to it. As long as the trace stays the same, I can do the replay on a new binary. So in this debug binary, I add a new print function in there so that I can do more debugging. And also that print function is whitelisted even though it's in the replay mode, I don't do the replay for that particular print. So let's see how this looks. With this build, I can run this with the original trace. So everything runs through, but you can see I have a new print function that's newly added, but it doesn't affect the original trace. So then that's why we can still rewrite and with more debugging for, or even writing things to the file system or something. Okay, so then, yeah, the tool is available in this link, and we are planning to add more use cases like access control or even building some adapters. Like if you have two WAIT files, then we can figure out how do you adapt from one WAIT interface to another. Another interesting use case is for PGO, like we can catch some production traffic online, and then offline we can do some profiling guided optimization. Without any runtime overhead, because everything can be done offline because we have the trace already. And also a lot of features like in the upcoming component model release will help this tool. So one thing that's kind of interesting is that this tool basically is kind of changing with Bytecode by adding more stub implementations, but we didn't do it in a with Bytecode code base directly. Instead, what we do is we take the result of the with Bytecode, like a binding.is file, and we take a look at the Rust generated Rust file to figure out what needs to be implemented. And then we are purely doing this on the Rust side. So this has pros and cons. One of the things we are not doing this in Bytecode is that this is kind of a special case of code generation. It's not a generic binding generation per se. So ideally, if you have a plugin system for Bytecode, then maybe we can do it there. But by doing this on the Rust side, it gives us more flexibility that we can do whatever we want. We can add more logics in here. And then we also didn't lose any information. Basically, by looking at the binding.is, we can recover the original WAIT types. Like every Rust type definition there corresponds back one-to-one to the original WAIT type. The only thing that's missing is the uppercase or lowercase ID that gets transformed, but that's just for documentation purpose. That's kind of the trade-off we are happy to get out here. And then also like another thing is that since we have instrumentation, then it happens sometimes that we need to import two exactly the same interface, but for different purposes. One is virtualized and the other is not virtualized. And currently we can express this in WAIT. So what we do here in the tooling is we rename these interfaces to have different names. But ideally, if we allow duplicate imports, then they will simplify the process here. And similarly for optional imports, that will help the WAG to like writing library code. Then sometimes imports is there, sometimes it's not, depending on the user. With like the actual code. So this will also help. Yeah, so like happy to take any questions here. And then if people are interested in trying out or collaborate, I'm happy to take questions from here.
Yeah, this is absolutely amazing. Especially like, the ideas of doing these proxy-like components, have been like floating around, but to see them all together in one super awesome CLI is incredible. And like, I want to use that fuzz mode. I thought it was pretty crazy. But yes, if people have questions, please throw them in the Zulip, and we'll answer those async. And with that, we've got our very last lightning talk of the day. Till, tell us how to write some good specs for WASI.
Hello. Yeah, writing good specs is very hard. So I'll not be able to give you a comprehensive overview of here are all the things you need to do to write a good spec, because it is just fundamentally very hard. What I do want to talk about is some tooling I built to make sort of the act of creating specifications a bit easier, because I do think that that is a major issue to overcome. To explain this, this is just a view of the WASI HTTP proposal. We have actually for the P2 version these markdown renderings of the WIT files here. And the WIT files at times, or the symbols in the WIT files contain doc comments, but that's basically, so these two things are basically what we have. And really, again, the markdown files are just generated from this. So this is the spec we have for WASI HTTP. These for P2, these 3 WIT files. For P3, it's these two files. And then the dependencies right here. That doesn't give implementers nearly everything they need to actually implement interoperable specifications. To demonstrate that, or show what other spaces do, here's the fetch spec for JavaScript or the DOM implemented in browsers, and by now actually most outside the browser JavaScript runtimes as well. Contains lots and lots of sort of infrastructure things, and then specification of the fetch API, including kind of an overview, non-normative notes for user or for developers using these APIs and so on. And then the web built-ins use this IDL called web IDL. So the web IDL definition for built-ins, I'll take the request one here, for example. And then if you look at the constructor here, you see something that we are missing. You see the algorithm needed to implement the constructor of request. And it's all kind of, it's this ordered list where if you want to make use of it or refer to it, you can in detail, obviously, I'll read it, but also have these nice features such as the ability to highlight things. There are references to other concepts that are being invoked. And for example, here, if you click on one of those, then you get a jump to the definition. If you click on the definition, you get a list of references to this to this concept. As you can see, the concept of request is shockingly used a lot in the fetch spec. We're pretty fundamentally missing. Basically, what we have is much more focused on these non-normative nodes, information about how to use the API, which is what should go in doc comments. I'll just quickly show for the WebAssembly core specification, that is what this looks like. It's a slightly different format from the fetch spec, but fundamentally it also has a similar kind of setup. So what I built is, starting with the first view, a viewer where this is the exact same content as in the WIT interface I showed earlier. except with a few things added to it, sort of a lot of kind of boilerplate. As you can see, it already looks kind of like a spec. But it's actually focused on documentation. Normative specification is here, except not actually implemented. But it's kind of hidden by default. I think that's actually already kind of a nice improvement. And as you can see in the URL, this is actually referring to exactly the proposal I showed earlier. There is nothing custom here. It's all generated from this. How is it generated? If I click on edit here, I get something else. I get the edit view. I can also here click on view real quick. That shows almost the same thing as the documentation thing, except this time the normative specifications are open. It's really just, I just want to read the spec. I don't want to work on it, but I don't just want to read the documentation either. Okay, but back to editing. This all, so now we have the widget interfaces or files from earlier. We also now have a spec.md file. And that contains lots of to-dos. And we can do something like I can type, but let's ignore that. We really can't type. And now we have this. I just put it as a bad example because it's now linking. Sorry, I'll add it. So anyway, the key point is we get something very similar to the output before. We can refer to other concepts here as well. Those will get auto-linked and all that. And if I reload this, this is all persisted, as you can see. How is it persisted? So basically, if I close the spec, I can see it created lots and lots of snapshots of this specification. But let's delete all of these. And now I'll go back and reload. And you saw really quickly what it did was it looked for WIT files in the URL I gave to the proposal. Then it saw, okay, there are WIT files. There's also a deps.toml file in there. I'll basically spider from here, discover all the dependencies, load all of those, and then interpret all that, and then scaffold this spec.md document. And ultimately, here, this is just a previewer that's automatically generated from the WIT files and the spec.md file based on information in the spec.wit.toml file. Spec.wit is a name I gave this tool. Yeah, so all of this, all that existed before I reloaded here were these WIT files and the deps.toml file, nothing else. So this is all generated, but I can edit it now. Right now, the flow, if I want to actually commit something, would be that I download a zip file, open and add that to some local Git checkout and open a pull request. Ultimately, maybe we can do a bit of a better integration with GitHub authentication. I don't know yet. All of this is also available as a CLI tool. So there's a spec.wit CLI tool. And this is really just an online interface for it. The spec.wit tool allows you to do spec.wit create, or new, I think. Spec.wit sync, where it reads a WIT file, sees whether there are added or changed or removed symbols in it, and then updates the outline of the spec.md file, just fitting in new things, remove things, but retaining otherwise the content. There's spec with serve, which, and I guess this is actually another part. You can see respec here. This is generated by by the same framework as the WebAssembly core specification uses, called respec, which does all of the symbol linking and tracking and so on. I just remembered. So we also have these permalink tables and so on. That is all maintained by SpecWid, by respec, based on information that SpecWid assembles and gives it, and ultimately spits out an input file that respec can then use and render the specification. So all that part I didn't have to do myself. To me, key point in this is all of these things like cross references and so on, including, I just realized, I should show, so we have here an import of an external symbol from another spec. If I click on that, I apparently broke this. I pushed an update earlier with some bug fixes, but I apparently broke the cross-linking. We'll have to fix that. Normally, it should have gotten you to a viewer for the that's navigated to the duration symbol in the clock spec. That's apparently broken right now. None of this in general is yet public because this is kind of a sneak peek for two reasons. One, I have some kind of obvious showstopper bugs to fix, such as some of this is actually some of the boilerplate in the documents is really just blind copy, nothing useful. I want to fix those things, and I want to present this to the WASI subgroup, because obviously, ultimately, I hope that people working in that group will make use of this to actually write specifications. Again, this is fundamentally and just intrinsically hard task, but I think with this kind of tooling, it's easier to get a start and to actually also see how are their specs structured. So would be very interested in, I guess in particular, once I make it public, I'll share that on Zulip, getting feedback, but also, and I'll stop sharing here, would love to hear people's thoughts on this in general.
I will allow 2 minutes of questions before we go to the wrap-up session.
I like how much more professional it looks. Looks like we're making real specs, so that's a great job.
Oh, one thing I forgot is, yes, as Bailey mentions, populated WASI dev. So what I'm imagining is that we could have links such as docs.wasidev /WASI HTTP or /HTTP, and or edit.wasidev /HTTP, things like that, and have that be integrated there.
We have 2 questions from Dave. Hopefully no one hears the dog in my microphone. There's 2 questions from Dave. First of which, how do you see the POSIX interfaces like file system or sockets being specified? I like the level of detail of the web specs, but for those POSIX-like interfaces, it ultimately boils down to we expose whatever the OS does with all of its quirks and oddities.
That's to some degree where the fundamentally hard part comes in, and it's not just writing spec algorithms is just difficult, because it's kind of like programming, except you can't run the result, and you have to hope that other people will do, and then inform you of maybe bugs in your program that you have. we, in addition, will have the issue that we don't even yet have very hard answers to where does the scope of WASI start or end. What do we bottom out in within WASI and say the rest is kind of implementation defined or specified over here, which for HTTP, that's going to be the answer for in a lot of cases. But for WASI KV, there's no specification to be had. So but also we can't fully define the exact semantics of every operation to the very end, because then it's unimplementable in terms of real world implementations of key value stores. So difficult questions to answer here, and for file systems, the same applies, obviously, but we don't know yet.
And there's a second question. Do we need to maintain this separately from the WIT files, or can it be integrated into the WITs themselves, or vice versa, to remove the double bookkeeping?
Initially, we actually tried to make this work. We had support for wit.md files, which were sort of little bit programming style interspersed documentation with code blocks, and it didn't work for various reasons that I think would take too much time to talk through. I actually think it is good for the WIT files to focus on describing the interface, and doc comments I think make sense in there, and then the lower level specification to have that in a separate document that not everybody ever needs to see. That's just, if you're a developer, you don't need using an API, you don't need the specification. It might make sense to have links to that, like MDN for web specs has links to the specification for everything it documents. But having that in the same document, I think, isn't actually desirable, because that would make the WIT spec for HTTP a very, very long document indeed, once we actually have a properly filled out spec. And so I think having these side by side would be good. Oh, and obviously my hope would be that eventually these spec.md files and the spec with manifest can also be in the WASI repo next to the WIT files in the same place. They shouldn't be maintained elsewhere.
Gotcha. Well, with that, folks, just a couple of things before we get you all out of here. So the main thing I want to say is thank you to all of our speakers for taking so much time to put all these presentations together, for taking time to come and give us these presentations. All of them were absolutely excellent. We thank you so much for that. And we appreciate all of the work in the Bytecode Alliance that you do that has come to this point that you are able to actually present it to us. Thank you to everyone who tuned in to the stream, either on YouTube or tuned into the Zoom. We really appreciate you coming and participating in the community. The Bytecode Alliance is exactly that. It's an alliance. We're all here together, working together, and us coming together is showcasing that we still have the power to keep on doing that. So that's fantastic. If you are a speaker and you have not yet posted your slides in the Zulip, I ask that you please do so. For everyone who's been watching, look out in the next couple of days. There's going to be a survey link that David is going to post in Zulip. And we please ask you to fill out that survey. We want to continue making these events better, whether they're virtual or they're in person. And the last thing I want to say is a very special thank you to Bailey and to David for doing the legwork to even have this event go off. So thank you for that. And with that, we conclude our Plumber Summit. Thank you so much, everyone. And please have a fantastic rest of your day and a fantastic weekend. Take care, everybody.